Hello there and welcome to Life Beyond Seen, where curiosity gets comfortable, questions slow their pace, and science is allowed to wander without needing to arrive anywhere too quickly. This is a place for thinking gently, for letting ideas stretch out instead of snapping to conclusions, and for following threads simply because they are interesting, not because they promise neat answers at the end. Tonight, we're turning our attention downward, not toward the stars or distant galaxies, but toward a place that exists right here on Earth, beneath the surface of the water you've probably looked at 1,000 times without ever suspecting how far it really goes. The ocean has a strange habit of pretending it's familiar. We swim in it, sail across it, photograph it in postcards and documentaries, give it soothing music and slow camera pans. It looks blue and calm from above, sometimes rough and dramatic, sometimes gentle enough to reflect the sky. But beneath that surface is a vertical world that drops away layer by layer, becoming colder, darker, quieter, and far more hostile than most places we associate with life or exploration. At the very bottom of that descent lies the Mariana Trench, the deepest known point in Earth's oceans, a place so extreme that even now, with satellites orbiting above us and robots exploring other planets, scientists still hesitate to go deeper into it. That hesitation isn't about fear in the dramatic sense. There are no sea monsters waiting with glowing eyes, no swirling vortices ready to pull ships under. It's a quieter kind of resistance, built from pressure, distance, cost, uncertainty, and the simple reality that some environments push back harder than our curiosity can comfortably handle. The Mariana Trench isn't just deep, it is relentlessly deep. It is deep in a way that resists human intuition, deep in a way that turns ordinary materials into fragile shells, and deep in a way that transforms time, sound, and movement into something unfamiliar. You might expect that a place like this would be a magnet for exploration. After all, humans have a long history of going where it's difficult, dangerous, or seemingly unnecessary. We climbed mountains before we understood altitude sickness. We crossed oceans without knowing what waited on the other side. We left the planet entirely and drifted through space, supported by machines that had to work perfectly every second. And yet, when it comes to the deepest part of our own oceans, progress has been slow, cautious, and remarkably limited. Only a handful of crude descents have ever reached the bottom, and most scientific work there relies on brief visits by unmanned vehicles if it happens at all. So why is that? Why, in an age where we can land probes on asteroids and map distant planets in detail, do scientists still hesitate to go deeper into the Mariana Trench? Why does this place remain largely untouched, rarely visited, and only partially understood? The answer isn't a single obstacle or a dramatic barrier. It's a layered story, much like the ocean itself, where each depth introduces new challenges that don't replace the old ones but pile on top of them. Before we drift further into that story, take a moment to notice where you are right now. Maybe you're listening late at night, with the lights dimmed and the day already starting to loosen its grip. Maybe it's early morning, and the world feels quiet but alert, like it hasn't quite decided what kind of day it's going to be. You might be at home, in bed, on a long drive, or sitting somewhere familiar enough that your mind can wander without worrying about what comes next. Wherever you are, there's a surface beneath you, solid and reassuring, separating you from whatever lies below. Now consider this. Beneath most places on land, if you dig deep enough, you eventually hit rock. Hard, stable, unyielding. The ocean doesn't offer that kind of certainty so easily. Beneath the water, depth isn't something you can see or feel until it presses back. It's a distance measured not in steps or miles, but in pressure, darkness, and isolation. The deeper you go, the less the surface matters. Light fades, sound behaves differently, and the familiar rules of the movement begin to change. If you find this kind of slow exploration soothing, or if these questions help your thoughts settle instead of racing, you're always welcome to let the video know with a like or a quiet subscription. It helps this calm corner of curiosity reach others who might need a place to let their minds drift, without being pulled in every direction at once. There's no rush though. This isn't a race to the bottom, it's more of a gradual descent, taken one careful step at a time. When people hear the phrase deepest place on Earth, it often sounds abstract, like a record in a book or a statistic on a chart. The Mariana Trench reaches nearly 11 kilometres below the surface, deeper than Mount Everest is tall. That number is impressive, but it doesn't really capture what that depth means. It's hard to picture a vertical drop that long, especially when most of us rarely experience depth beyond a swimming pool or the shallow coastal waters where sunlight still dances on the sand. Imagine lowering something slowly into the ocean. At first, everything feels normal. Light filters down, colours remain recognisable, and the water feels like water. Go a little deeper, and the red hues disappear. Go deeper still, and even blue fades into a dim uniform grey. Eventually there is no natural light at all. The water becomes a cold, black expanse, broken only by the occasional glow of organisms that make their own light because nothing else reaches them. Now add pressure. For every 10 metres you descend, the pressure increases by about 1 atmosphere. That's the same pressure you feel at sea level from the air around you. At the bottom of the Mariana Trench, the pressure is more than 1,000 times what we experience on land. It's enough to crush unprotected objects instantly, to force water into places it doesn't belong, and to turn tiny flaws in materials into catastrophic failures. This isn't a problem you can solve with thicker walls alone. Every additional layer adds weight, complexity, and new points of failure. This is where the story of hesitation begins. Going deeper isn't just a matter of building something stronger. It's a matter of building something that can survive a world that actively tries to erase empty space. The ocean doesn't simply sit there at those depths. It presses inward from all directions, constantly, without pause. There is no moment of relief, no gradual easing. Once you're down there, the pressure is total. Distance adds another layer of difficulty. The Mariana Trench isn't just deep, it's remote. It lies in the western Pacific Ocean, far from major ports and easy support. Reaching the area requires long voyages, careful planning, and significant resources before any descent even begins. Once a vehicle starts going down, it's effectively on its own. Communication becomes slower and less reliable. Real-time control is limited. If something goes wrong, there is no quick rescue, no nearby backup waiting to intervene. There's also the question of return. Going down is only half the journey. Everything that descends must also come back up, carrying data, samples, or people with it. Designing systems that can handle both directions under extreme conditions is far more complex than building something meant to stay put. The ascent introduces its own stresses, temperature changes, and mechanical challenges that don't always get the same attention, but are just as unforgiving. And then there's the matter of value. This is perhaps the most uncomfortable part of the discussion, because it forces scientists and funding agencies to make choices. Every deep-sea expedition costs a great deal of money, time, and effort. Ships must be crewed and maintained. Specialized vehicles must be built, tested, and repaired. Teams of engineers, scientists, and support staff must work together for months or years to make a single descent possible. All of this for a place that, at first glance, appears empty, silent, and unchanged. What do we gain from going deeper into the Mariana Trench? The answer isn't nothing, but it isn't always obvious either. We already know it's deep. We know it's dark. We know the pressure is extreme. We know there is life, but sparse and specialized. Each new visit adds details, not dramatic revelations. For institutions tasked with allocating limited resources, it can be difficult to justify repeated descents when other projects promise clearer, more immediate results. This doesn't mean scientists lack curiosity about the trench. Quite the opposite. The hesitation comes from respect, not indifference. The Mariana Trench represents a boundary, a reminder that not every part of our planet is easily accessible, even with advanced technology. It forces us to confront the limits of our tools and the assumptions we make about exploration itself. There's also a psychological aspect that rarely gets discussed openly. Humans evolved on land, under open skies, surrounded by air. Even in controlled environments, the idea of descending into a dark, crushing void triggers something deep and instinctive. Space is dangerous, but it's also expansive. There's room to move, to orient yourself, to see distant points of reference. The deep ocean offers none of that. It closes in, limits perception, and removes nearly all sensory feedback except what your instruments provide. When scientists talk about the Mariana Trench, they often emphasize caution. Not because they are afraid of the unknown, but because the unknown there is combined with an environment that allows very little margin for error. A single mistake, a tiny failure can end an expedition instantly. That kind of risk demands a level of confidence and redundancy that is difficult and expensive to achieve. As we ease further into this topic, it's worth remembering that the Mariana Trench isn't a single place you can point to on a map and say, that's it. It's a long, curved scar in the Earth's crust, stretching for thousands of kilometers. The deepest point, known as Challenger Deep, is just one part of a much larger system, shaped by tectonic forces that are still active today. The trench is slowly changing, shifting, and evolving on timescales that don't match human schedules or funding cycles. This dynamic nature adds yet another complication. Instruments left behind may not behave as expected. Conditions measured on one descent may differ on the next. The seafloor itself can move, collapse, or rearrange. Unlike a laboratory, the trench doesn't stay still for your convenience. All of this sets the stage for the central question we'll keep circling, from different angles and depths as we continue. Why do scientists still hesitate to go deeper? Not once, but again and again. Not as a dramatic refusal, but as a quiet pause, a careful calculation, a decision to wait until the tools, the questions, and the reasons align just a little better. The ocean doesn't mind waiting. It has been deep for millions of years, and it will remain so long after our current technologies become obsolete. For now, we stand at the surface, looking down through layers of water and uncertainty, deciding how far our curiosity is willing to travel and what we are prepared to risk when the bottom pushes back. When people imagine deserts, they tend to picture heat, sand, and endless horizons shimmering under a bright sun. It's a useful image because deserts are defined less by temperature and more by scarcity. Little water, little life, long stretches where almost nothing seems to happen. In that sense, the deepest parts of the ocean qualify just as much as any arid landscape on land. Beneath the waves, far below where sunlight fades and familiar marine life disappears, stretches a blue desert that covers most of the planet. Vast, quiet, and largely untouched. From the surface, the ocean feels alive and dynamic. Waves roll in patterns that never quite repeat. Currents carry warmth and nutrients across entire hemispheres. Fish flash beneath the surface, birds dive from above, and human activity leaves trails of noise, light, and motion. But as you descend, layer by layer, that activity thins out. The ocean doesn't gradually transition into emptiness. It sheds complexity step by step, like a city giving way to suburbs, then farmland, then wilderness, until eventually there's nothing left but open space. The first few hundred meters are deceptively rich. Sunlight still penetrates here, allowing photosynthesis to occur. This is where most ocean life resides, clustered around energy flowing down from the sun. Plankton blooms support fish. Fish support larger predators, and entire ecosystems stack themselves vertically in relatively shallow water. From a biological perspective, this zone carries a disproportionate amount of the ocean's activity. It's busy, crowded, and constantly changing. But even here, the signs of limitation are already present. Light weakens quickly with depth. Colours fade in a predictable order. Reds vanish first, then oranges and yellows, until only blues remain. This isn't because blue is somehow more abundant, but because water absorbs longer wavelengths more efficiently. What reaches deeper layers is filtered, narrowed, simplified. The ocean begins reducing the information available to anything living within it. Below this sunlit layer lies a region where the last traces of natural light struggle to survive. Photosynthesis stops. Life continues, but it does so on borrowed energy. Organisms feed on what sinks from above, a slow rain of organic debris known as marine snow. Dead plankton, waste, fragments of plants and animals all drift downward, feeding whatever waits below. It's not a generous supply. It's thin, inconsistent, and unreliable. In this environment, efficiency becomes everything. As depth increases, the ocean begins to resemble a desert more clearly. Food is scarce. Movement costs energy. Growth is slow. Many organisms adopt strategies that would seem extreme in other environments. They conserve motion, stretch lifespans, and reduce unnecessary complexity. Some develop enormous mouths relative to their bodies, ready to seize rare opportunities. Others glow faintly in the dark, using bioluminescence to attract prey, or communicate in a world where sound and light behave differently. Eventually, even this tenuous web thins out. The deep ocean floor, including the region surrounding the Mariana Trench, receives only a tiny fraction of the energy produced at the surface. It's estimated that less than 1% of surface productivity makes it to the abyss. That means life here exists at the edge of what's biologically sustainable. Every calorie matters. Every adaptation is the result of intense selective pressure over millions of years. From a human perspective, this environment feels empty. But emptiness can be misleading. The desert beneath the waves is not lifeless. It is sparse. It's a place where events happen slowly and quietly, where change is measured in centuries rather than seasons. For scientists accustomed to environments where processes unfold on human timescales, this creates a challenge. Studying systems that move so slowly requires patience, long-term observation, and a willingness to accept that results may not be immediate or dramatic. This scarcity is one of the reasons scientists hesitate to push deeper into the Mariana Trench. Exploration thrives on feedback. You go somewhere, you see something, you learn, and that learning informs the next step. In the deep ocean, feedback is minimal. A descent that takes hours may yield only a few hours of observation time at the bottom. Cameras capture darkness punctuated by occasional movement. Sensors record pressure, temperature, and chemistry that change very little from one moment to the next. That doesn't mean the data isn't valuable. It is, but its value is subtle. It accumulates slowly, requiring context from many missions over long periods. For institutions under pressure to demonstrate progress, to produce visible outcomes, this kind of work can be difficult to sustain. The blue desert doesn't reward curiosity quickly. There's also the matter of scale. The deep ocean covers an enormous area. The Mariana Trench alone stretches farther than many countries. A single descent explores a tiny point, like dropping a probe into the Sahara and trying to understand the entire desert from that one location. Patterns exist, but they are hard to detect without extensive coverage, and extensive coverage at extreme depths is prohibitively expensive. This scale problem is compounded by the environment's uniformity. At the surface, ecosystems vary dramatically over short distances. Reefs, kelp forests, open water, and coastal zones all sit near one another, each with distinct characteristics. In the deep ocean, differences are subtle. A slope here, a sediment type there, a slight variation in chemistry. To non-specialists, images from different deep-sea locations often look nearly identical. Dark, flat, quiet. This sameness makes it harder to justify repeated exploration to those outside the field. The desert analogy extends to sound as well. At depth, sound travels differently. It can propagate over long distances, bending and reflecting through layers of water with varying temperature and density. but the environment itself produces very little noise. There's no wind, no waves, no rustling vegetation. What sound exists comes from distant geological activity, occasional biological signals, or human-made sources far above. This silence is part of what makes deep-sea exploration psychologically demanding. Humans are used to environments that provide constant sensory feedback. Silence, especially prolonged silence, can be disorienting. The pressure adds another layer of isolation. Everything in the blue desert exists under a crushing weight that never lets up. Materials behave differently. Metals compress. Plastics stiffen or fail. Seals that work perfectly at shallow depths can leak or rupture. Electronics must be carefully protected, often encased in thick housings filled with oil or pressure-resistant fluids. Every additional component increases complexity, and complexity increases the risk of failure. Because of this, deep-sea vehicles are often designed to be as simple as possible. They move slowly, perform limited tasks, and prioritize survival over flexibility. This is very different from the exploratory vehicles used in space, which often emphasize maneuverability and versatility. In the trench, survival is the first requirement. Exploration is secondary. The blue desert also challenges assumptions about habitability. On land, deserts are harsh but still accessible. With the right equipment, humans can traverse them, set up camps, and conduct long-term studies. The deep ocean does not allow this. There is no equivalent of a base camp at 11 kilometers down. Every visit is temporary. Every instrument deployed must either return to the surface or be left behind, potentially unrecoverable. This temporary nature limits the kinds of questions scientists can ask. Long-term experiments are difficult. Continuous monitoring is rare. Most data comes from snapshots, brief glimpses separated by long intervals. This makes it harder to understand processes that unfold over long timescales, such as geological shifts, slow biological growth, or gradual chemical changes. Despite these challenges, the blue desert holds important clues about Earth's systems. It plays a role in carbon storage, heat distribution, and the long-term stability of the climate. Sediments at the bottom of trenches preserve records of past events, from volcanic eruptions to asteroid impacts. Life here pushes the boundaries of what biology can tolerate, offering insights into adaptation and resilience. And yet these insights often come indirectly. Samples retrieved from depth are analysed in laboratories far removed from their original environment. Conditions are approximated, simulated, inferred. Direct, prolonged observation remains rare. This distance between subject and observer adds uncertainty, and uncertainty breeds caution. There's also an emotional element that's easy to overlook. The deep ocean doesn't inspire the same sense of possibility as space. Space feels open, expansive, filled with destinations waiting to be reached. The blue desert feels closed, inward, compressive. It doesn't invite, it resists. For explorers, this resistance changes the tone of the mission. It becomes less about discovery and more about endurance. Historically, human exploration has favoured environments that offer at least the illusion of progress. You climb a mountain and reach a summit. You cross an ocean and arrive at land. You launch a spacecraft and orbit a planet. In the Mariana Trench, there is no vista at the bottom, no dramatic reveal, just more darkness, more pressure, more silence. The achievement is real, but it's subtle, experienced mostly through instruments and data readouts. This subtlety affects public perception. Funding, attention, and enthusiasm often follow spectacle. A rover on Mars sends back images that are immediately compelling. A deep-sea probe sends back images that require explanation, context, and patience to appreciate. Without a broad audience ready to engage with that subtlety, support can waver. Still, scientists continue to return to the blue desert, drawn by questions that refuse to go away. How does life persist under such extreme conditions? What unknown chemical processes occur in these depths? How does the deep ocean interact with the rest of the planet over geological time? These questions don't demand immediate answers, but they remain unanswered nonetheless. As we move deeper into this exploration, it becomes clear that hesitation doesn't mean avoidance. It means selecting moments carefully, choosing tools deliberately, and acknowledging that some environments require a different rhythm of inquiry. The blue desert beneath the waves isn't going anywhere. It waits, unchanged by human schedules, offering its secrets slowly, to those willing to approach on its terms rather than their own. And it's within this quiet, sparse landscape that the Mariana Trench asserts itself most strongly, not as a singular destination, but as the deepest expression of a world that operates by rules very different from the surface we know so well. Depth is one of those concepts that feels straightforward until you try to hold it in your mind for more than a moment. We measure it easily enough. Meters, kilometers, miles. Numbers stack neatly on top of one another, giving the impression that depth is just distance turned vertical. But when scientists talk about how deep the Mariana Trench really is, they're not just talking about a number. They're talking about a place where human intuition stops being useful, where familiar comparisons break down, and where distance turns into something that reshapes physics, biology, and technology all at once. At first glance, the depth of the Mariana Trench sounds impressive in a simple way. Nearly 11 kilometers from the surface to the deepest point. Deeper than Mount Everest is tall. That comparison gets used often because it feels dramatic and accessible. You can picture a mountain. You can imagine climbing it, or at least standing at its base and looking up. Flip that mountain upside down, submerge it in water, and you get a rough sense of the trench. Rough, but still incomplete. The problem is that height and depth don't behave the same way in human experience. Height gives you perspective. You can see farther. The air thins, but the sky opens up. Even danger comes with views, with orientation, with a sense of where you are relative to everything else. Depth takes those reference points away. The deeper you go, the less you can see, the less you can hear, and the less useful your instincts become. Distance downward doesn't reveal more of the world, it removes it. When scientists say deep, they're rarely talking about a single threshold. The ocean is divided into layers not because the water itself changes colour or texture in neat bands, but because conditions shift in ways that matter. Temperature drops, pressure increases, light fades, chemistry shifts, life adapts or disappears. Each of these changes happens gradually, but together they create zones that feel fundamentally different from one another. The first few hundred meters already challenge assumptions. Even here, sunlight weakens enough to change how ecosystems function. Past this point, depth begins to influence biology in obvious ways. Past 1,000 meters, light is essentially gone. Past several thousand, temperature stabilizes near freezing. By the time you approach the depths of the Mariana Trench, the environment has become so stable, so uniform, that variation itself becomes rare. But stability doesn't mean simplicity. At these depths, pressure dominates everything. It's difficult to convey just how absolute that pressure is. On land, pressure comes from the air above you, but air is light. It compresses easily. Water is heavy and it does not give way. At the bottom of the trench, every square centimetre of surface is supporting the weight of a column of water taller than most mountains. That weight never shifts, never relents. If you could somehow stand there, unprotected, you wouldn't feel the pressure building gradually. There would be no moment of realization. Your body would simply fail. The pressure would force water into places it does not belong, collapse air-filled spaces, and overwhelm structural integrity faster than nerves could register pain. This is why depth in the ocean isn't something humans can directly experience the way we experience altitude or temperature. It's either managed perfectly or it's fatal. For scientists and engineers, this changes how depth is approached. Going deeper doesn't just mean adding more fuel or stronger motors, it means redesigning everything from the ground up. Materials that work well at shallow depths become liabilities. Steel that seems solid on the surface may flex or fracture. Seals that hold against moderate pressure may deform or leak. Electronics that function flawlessly in laboratories may short-circuit when compressed or exposed to cold. This is why the phrase "how deep is deep" really isn't rhetorical. It's a practical question with real consequences. At what point does the cost of going deeper outweigh the benefits? At what depth do existing tools stop working reliably? At what depth does risk increase faster than knowledge gained? The Mariana Trench sits well beyond many of these thresholds. It's not just deeper than most of the ocean. It's deeper than most technologies were ever designed to handle. Early deep-sea exploration vehicles weren't built with 11 kilometers in mind. They were built incrementally, pushing boundaries step by step. Each step required new engineering solutions, new testing methods, new safety margins. Even today, only a small number of vehicles are capable of reaching the trench's deepest point. Most oceanographic equipment operates far above it. Sensors, cameras, and sampling devices are often rated for depths that seem extreme but fall short of the trench. That means much of what scientists know about the deep ocean comes from places that are deep, but not deepest. This distinction matters. Conditions at 6,000 meters are severe, but they are not the same as conditions at 11,000. Pressure nearly doubles, temperature differences flatten out, sediment composition changes, biological communities become even more specialized. Small differences that seem negligible on paper become significant when layered over such extremes. Another way depth complicates understanding is time. At the surface, time feels immediate. Weather changes daily. Seasons shift visibly. Biological cycles play out quickly. At depth, time stretches. Sediments accumulate slowly, sometimes millimeters per 1,000 years. Chemical changes happen over geological timescales. Biological growth can be incredibly slow, with some deep-sea organisms living for centuries. This slow pace means that deep also implies ancient. The bottom of the Mariana Trench preserves records of Earth's past that are inaccessible elsewhere. Layers of sediment trap evidence of volcanic eruptions, climate shifts, and even cosmic events like asteroid impacts. Reading these records requires careful sampling and interpretation, often from tiny amounts of material retrieved at great cost. But retrieving those samples is itself constrained by depth. Drilling at 11 kilometers below the surface is not trivial. The equipment must withstand not only pressure, but also the challenge of operating precisely in an environment where direct human oversight is impossible. Every action must be planned in advance. Every failure risks losing not just data, but the equipment itself. Communication adds another dimension to depth. Radio waves do not travel well through water, especially at great depths. Communication with deep-sea vehicles relies on acoustic signals, which are slow and limited in bandwidth. Commands take time to reach a vehicle, data takes time to return. Real-time control is impossible. Scientists must trust pre-programmed instructions and hope that conditions don't deviate too far from expectations. This delay changes how exploration is conducted. In space missions, communication delays are expected, but the environment is comparatively predictable. In the deep ocean, conditions can vary subtly but meaningfully. A slope steeper than anticipated, sediment softer than expected, or an unexpected current can alter a mission's outcome. With limited ability to intervene, depth magnifies uncertainty. Depth also affects human perception indirectly. When scientists analyze data from the trench, they're interpreting signals that have traveled long distances through hostile conditions. Sensor readings must be corrected for pressure and temperature effects. Images captured under artificial light must be interpreted carefully, as colors and contrasts behave differently. Even basic measurements like distance and orientation can be skewed. All of this contributes to a kind of cognitive depth as well. Understanding the trench requires layering information from physics, chemistry, biology, and geology. No single discipline can fully explain what happens there. Depth forces collaboration, but collaboration introduces complexity. Different fields have different priorities, methods, and expectations. Aligning them around a place that yields slow, subtle data is challenging. There's also the issue of comparison. Humans understand scale through analogy. We compare unfamiliar things to familiar ones. But depth resists easy analogy. You can say the trench is deeper than Everest is tall, but that doesn't tell you how it feels, how it behaves, or why it matters. You can say pressure is 1,000 times greater than at the surface, but numbers like that lose meaning without context. Scientists often struggle with this when communicating their work. How do you convey the significance of an environment that few people will ever see, that doesn't produce dramatic visuals, and that operates on timescales far removed from daily life? Depth becomes not just a physical challenge, but a narrative one. This narrative challenge influences funding, public interest, and long-term commitment. Projects that promise clear milestones and visible outcomes tend to attract support more easily. Deep-sea research, especially at extreme depths, often promises only incremental progress. That doesn't make it less important, but it does make it harder to sustain in a world driven by short-term results. Yet depth continues to exert its pull. The question, how deep is deep, really persists because it's not just about measurement, it's about limits. How far can we push materials? How far can we extend remote operation? How much uncertainty can we tolerate? How patient can we be in the pursuit of understanding? The Mariana Trench sits at the far edge of these questions. It's deep enough that even reaching it feels like an achievement. Going deeper into understanding what happens there requires not just physical descent but conceptual adjustment. Scientists must think differently about time, scale, and reward. As we continue easing downward through this topic, depth will keep reappearing in different forms. Depth as pressure, depth as distance, depth as isolation, depth as time. Each one adds another reason why the trench remains largely unexplored, not because it is impossible, but because it demands a kind of exploration that runs counter to many of our habits and expectations. And as with the blue desert above it, the depth itself doesn't care whether we understand it or not. It remains, quietly, insistently deep, waiting without urgency while we decide how much of ourselves we're willing to send down to meet it. Pressure is one of those forces that feels abstract until it suddenly isn't. On land, it's easy to forget it exists at all. Air presses on us constantly, but because it presses evenly and gently, our bodies evolve to ignore it. We don't feel the atmosphere resting on our shoulders. We don't notice the weight of the sky. It's only when pressure changes abruptly, during a fast elevator ride, a flight or a dive underwater, that it briefly announces itself with a pop in the ears or a tightness in the chest. Then it fades again, returning to the background where it usually stays. The deep ocean does not allow pressure to fade into the background. It dominates everything. It defines what can exist, what can move, what can survive, and what can be built. When scientists talk about the crushing weight of the ocean, they are not speaking metaphorically. They mean it in the most literal sense possible. The deeper you go, the more the ocean behaves less like a place and more like a force. Water is heavy. That's easy to forget because we're used to interacting with it in small amounts. A glass of water, a shower, a swimming pool. But stack enough water on top of itself, and its weight becomes overwhelming. Every 10 meters of depth adds roughly 1 atmosphere of pressure. That's the same pressure exerted by the entire column of air above you at sea level. At 100 meters, you're under about 11 atmospheres. At 1,000 meters, over 100. By the time you reach the bottom of the Mariana Trench, the pressure exceeds 1,000 atmospheres. Numbers like that are difficult to internalize. They don't translate well into everyday experience. so scientists often try analogies. They might say it's like having dozens of jumbo jets stacked on a postage stamp-sized area, or like balancing the weight of a skyscraper on a human fingertip. These comparisons are useful, but they still fall short because they imply something sudden or localized. The ocean's pressure is neither. It is total. It presses from all directions at once, without gaps, without edges, without relief. This omnidirectional nature of pressure is what makes it so destructive to unprotected objects. On land, structures fail when forces are uneven. A building collapses because one part gives way before another. Under extreme pressure, failure is more subtle and more unforgiving. Any tiny weakness becomes the point where the ocean pushes its way in. A microscopic crack, an imperfect seal, a material flaw invisible to the naked eye can become catastrophic. For humans, this environment is completely intolerable. Our bodies rely on internal spaces filled with air, lungs, sinuses, ears. These spaces allow us to breathe, hear, and balance. Under extreme pressure, these spaces collapse. Water is forced into tissues. Blood chemistry changes. Even if oxygen were somehow supplied, the body itself cannot function when compressed beyond certain limits. This is why no human has ever gone to the deepest parts of the ocean without the protection of a rigid sealed vessel. That vessel, in turn, becomes the focus of intense engineering effort. Designing something that can survive such pressure is not just about making it thick. Thickness adds weight, and weight creates its own problems. Heavier vehicles require more energy to move. They sink faster, which might sound useful, but they also become harder to control. Structural strength must be balanced against buoyancy, maneuverability, and the ability to return to the surface. Early deep-sea submersibles learned this lesson quickly. The first attempts to reach extreme depths involve simple shapes, spheres, and near-spheres, because geometry matters under pressure. A sphere distributes force evenly, minimizing stress points. Flat surfaces and sharp angles concentrate stress, making failure more likely. This is why the deepest diving crewed vehicles ever built used thick-walled steel or titanium spheres to house their occupants. Even with optimal shapes, materials face limits. Steel is strong, but it compresses slightly under pressure. Over many cycles of descent and ascent, this compression can lead to fatigue. Titanium offers advantages, but it is expensive and difficult to work with. Composites behave unpredictably at extreme depths. Every material choice is a compromise, weighed against cost, reliability, and performance. Pressure doesn't only threaten structures, it affects systems in subtle ways. Electrical connectors can fail as insulating materials compress. Lubricants thicken or stop working altogether. Mechanical joints seize. Hydraulic systems behave differently when external pressure rivals internal pressure. Even glass, something we think of as rigid, behaves strangely. Thick acrylic windows used in deep-sea vehicles can flex inward by several centimeters under pressure, bowing like a living thing responding to the ocean's weight. For unmanned vehicles, pressure still sets hard limits. Electronics must be protected, often by enclosing them in pressure-resistant housings or filling compartments with oil that transmits pressure evenly. Batteries must function in cold, high-pressure environments. Sensors must remain accurate even as their components compress. Each additional system increases complexity, and complexity increases the chance that something will go wrong. This is one reason scientists are cautious about repeated descents into the Mariana Trench. Every dive carries risk, not just to expensive equipment, but to the data itself. A failed mission might return nothing at all. Worse, it might leave equipment irretrievably lost on the seafloor, adding to the very human debris that has already reached even the deepest parts of the ocean. Pressure also limits how long a vehicle can stay at depth. Even if a submersible survives the descent, prolonged exposure increases the likelihood of failure. Materials creep. Seals degrade, tiny leaks can develop, And at those pressures, a leak is not a slow drip. It is an implosion waiting to happen. For this reason, most deep dives are short. Vehicles descend, perform their tasks, and ascend as soon as possible. This short window restricts scientific observation. Processes in the deep ocean often occur slowly. Biological interactions may be infrequent. Geological changes may be subtle. Chemical gradients may shift over long periods. A few hours on the bottom is enough to collect samples and images, but not enough to fully understand dynamic systems. Pressure, by limiting time, limits knowledge. There's also the problem of testing. You can't easily simulate the pressure of the Mariana Trench on land. Specialized pressure chambers exist, but they are small and limited. Testing full-scale vehicles under realistic conditions is difficult and expensive. Much of the engineering relies on models, calculations, and incremental testing at shallower depths. This introduces uncertainty. Until a vehicle actually makes the dive, you don't know for certain how it will behave. That uncertainty weighs heavily on mission planners. Unlike space missions, where conditions can often be modelled with high accuracy, the deep ocean introduces variables that are hard to predict. Temperature gradients, unexpected currents, sediment clouds stirred up by the vehicle itself. Pressure amplifies the consequences of every unknown. When something unexpected happens, there may be no way to respond. Pressure also affects the environment being studied. Sampling organisms from extreme depths often kills them instantly as they are brought to the surface. The rapid drop in pressure causes gases to expand, tissues to rupture, and cellular processes to fail. Even if an organism appears intact, its internal chemistry may be irrevocably altered. This makes it difficult to study deep-sea life in its natural state. To address this, scientists have developed pressure-retaining samplers that keep organisms at depth-equivalent pressure during retrieval. These devices are complex, expensive, and limited in capacity. They work, but only for small samples. Studying larger organisms or ecosystems in situ remains a major challenge. Pressure, again, enforces its boundaries. The crushing weight of the ocean also shapes geological processes. At great depths, rocks behave differently. Sediments compact into dense layers. Faults move slowly but powerfully. The trench itself exists because one tectonic plate is being forced beneath another, a process driven by immense forces acting over millions of years. Pressure is not just an obstacle here, it is the architect. Understanding these geological processes requires direct measurement. Seismometers, pressure sensors, and long-term monitoring equipment would ideally be placed at depth and left there for years, but deploying and maintaining such instruments under extreme pressure is difficult. Many instruments fail before they can collect meaningful data. Recovering them adds another layer of risk. This is where the hesitation to go deeper becomes clearer. Pressure is not a single problem to be solved once. It is a constant presence that complicates every aspect of exploration. It increases cost, reduces reliability, shortens mission duration, limits sampling, and amplifies uncertainty. Each additional kilometre of depth doesn't just add more pressure, it multiplies these challenges. There's also a human factor at play. Scientists and engineers are trained to manage risk, not eliminate it. In the Mariana Trench, the margin between success and failure is razor thin. When missions fail, they do so decisively. There are no partial recoveries, no easy fixes. This reality encourages caution, especially when lives might be involved. Even for unmanned missions, the emotional impact of failure is real. Years of work can vanish in an instant. Funding agencies may hesitate to support follow-up missions. Public interest may wane. Pressure doesn't just crush objects, it can crush momentum. Yet, despite all of this, exploration continues. The crushing weight of the ocean has not stopped scientists entirely. It has simply forced them to proceed slowly, deliberately, and selectively. Each descent into the trench represents the culmination of careful planning, technological refinement, and acceptance of risk. As we move forward in this exploration, pressure will remain a recurring theme, not as an abstract concept, but as a tangible force shaping decisions. It explains why space, despite its dangers, often feels more accessible. It explains why the deepest parts of our own planet remain largely unseen. And it reminds us that curiosity alone is not always enough. Sometimes the environment itself sets the terms, and the ocean's terms are heavy, unyielding, and always pressing inward. Darkness is often treated as a simple absence, the lack of light, a condition that can be fixed by flipping a switch or waiting for sunrise. On land, darkness is temporary and negotiable. Night falls, but morning follows. Even in the deepest night, artificial light can recreate familiarity. Streetlights glow, screens flicker, rooms fill with soft illumination. Darkness becomes an atmosphere rather than a barrier. In the deep ocean, darkness is something else entirely. It is not an event or a phase. It is a permanent state that reshapes everything within it. Once sunlight disappears beneath the surface, it does not gradually return. There is no dawn in the deep ocean, no hint of morning waiting just beyond the horizon. The darkness below a certain depth is complete and unbroken, stretching not just for hours or days, but for millions of years. Nothing there has ever known light from the sun. Nothing evolved with the expectation that brightness might one day come back. This permanence changes the rules, and those changes ripple outward into biology, perception, technology, and the way scientists think about exploration itself. Light is not just a convenience, it is a primary organizing force for life on Earth. On the surface, nearly every ecosystem is structured around it. Plants use it to create energy. Animals time their behavior around it. Entire biological clocks are synchronized to the cycle of day and night. Even human culture is shaped by light, from work schedules to sleep patterns to the language we use to describe clarity and understanding. Remove light completely, and you don't just lose visibility, you lose orientation, you lose rhythm, you lose a shared reference point that connects organisms to one another and to their environment. In the deep ocean, darkness strips the world down to fundamentals. Energy must come from somewhere else. Communication must find other channels. Survival becomes less about reacting quickly and more about enduring patiently. For scientists, this presents an immediate challenge. Most of the tools we use to observe the world depend on light. Cameras, microscopes, telescopes, even the human eye itself all rely on photons bouncing off surfaces and returning information. In darkness, observation becomes invasive. To see anything at all, you must introduce light artificially. And introducing light changes the environment you're trying to study. This is one of the central paradoxes of deep-sea research. The act of observation alters the system. When a submersible turns on its lights, the darkness that has persisted for geological time is suddenly interrupted. Organisms that evolved to live without light react in unpredictable ways. Some flee, some freeze. Some are drawn toward the brightness, mistaking it for bioluminescent signals associated with food or mates. The scene you record is no longer neutral, it is a response to intrusion. This makes interpretation difficult. When scientists analyze footage from deep-sea dives, they must constantly ask whether what they are seeing is typical behavior or an artifact of the observation itself. In shallow water, this problem exists too, but its effects are easier to contextualize. In the trench, where encounters are rare and opportunities limited, uncertainty lingers. Darkness also changes how sound behaves, which in turn affects how information travels. In the absence of light, sound becomes the primary medium for long-distance communication and navigation. Many deep-sea organisms rely on vibrations rather than vision. They sense movement, pressure changes, and subtle shifts in water flow. For them, darkness is not blindness, it is normality. Human-made systems, however, are not optimized for this. Sonar can map terrain and detect objects, but it provides a different kind of information than vision. Sonar images are abstract, requiring interpretation and translation. They lack the intuitive immediacy of sight. A camera image feels familiar. A sonar map feels technical. This difference matters when scientists are trying to make sense of complex environments quickly. The reliance on sonar also introduces its own complications. Sound waves can disturb marine life. They can interfere with natural communication channels. In extreme cases, intense sonar has been linked to disorientation and harm in some species. While deep-sea research uses far lower intensities than military sonar, the concern remains. Darkness forces trade-offs between seeing and disturbing, between learning and altering. Navigation becomes another challenge. On land, darkness complicates movement, but landmarks remain. Stars, terrain, infrastructure all provide orientation. In the deep ocean, there are no visible landmarks. The seafloor may appear flat and uniform for long stretches. Without light, a vehicle can drift without realizing it. Even with instruments, maintaining precise position is difficult. Currents are subtle but persistent. Over time, they can push a submersible far from its intended path. This difficulty in navigation increases risk. A vehicle that becomes disoriented may collide with the seafloor, stir up sediment, or become trapped against a slope. In darkness, recovery is harder. There is no visual cue to guide corrective action. Everything depends on sensors and calculations, and sensors can fail. Darkness also affects scale. Without visual reference points, it is hard to judge size and distance. Objects can appear closer or farther away than they are. Small movements can seem large, and large movements can go unnoticed. This complicates sampling. A robotic arm reaching for a sediment core must rely on precise measurements, because visual estimation is unreliable. For crewed submersibles, darkness introduces a psychological dimension. Humans are visual creatures. Vision dominates our perception and provides reassurance. In complete darkness, even with artificial light, that reassurance is fragile. The illuminated area is small, surrounded by infinite blackness. Beyond the reach of the lights, nothing is visible. This creates a sense of confinement that is difficult to ignore. Even experienced explorers report that deep-sea darkness feels different from darkness on land or even in space. In space, there are stars, distant points of light that suggest openness. In the trench, darkness is close. It presses in from all sides, broken only by the narrow cone of a spotlight. There is no sense of distance beyond what the instruments tell you. This psychological strain matters because it influences how long humans can operate effectively in such environments. Fatigue sets in more quickly. Stress responses become harder to manage. Decision-making can be affected. These factors don't make deep-sea exploration impossible, but they add to the list of reasons why scientists approach it cautiously. Darkness also reshapes biology in profound ways. Without sunlight, photosynthesis is impossible. This removes the primary energy source for most life on Earth. In the deep ocean, energy arrives indirectly, either as organic material sinking from above or as chemical energy released from the Earth itself. Some ecosystems near hydrothermal vents rely on chemosynthesis, where bacteria use chemicals like hydrogen sulfide instead of light to produce energy. These communities are fascinating because they demonstrate that life does not require sunlight in the way we once assumed, but they are localized and rare. Most of the trench does not benefit from such energy-rich environments. As a result, many deep-sea organisms live in a state of extreme energy conservation. Movement is minimized. Growth is slow. Reproduction may be infrequent. Darkness supports these strategies by removing the need for visual displays or rapid responses. There is no advantage to bright colors or elaborate patterns. Instead, transparency, darkness, and subtlety prevail. Bioluminescence becomes one of the few ways light re-enters this world, but it is light on the organism's terms. It is controlled, brief, and purposeful. A flash to startle a predator, a glow to attract prey, a signal to communicate. This light is not meant to illuminate the environment. It is meant to convey information. For scientists, bioluminescence is both a gift and a challenge. It provides evidence of life in an otherwise dark environment, but it is unpredictable. Many organisms only produce light under specific conditions. The presence of a submersible may trigger or suppress these displays. Capturing them requires patience and luck. Darkness also complicates the study of change over time. On the surface, visual cues make it easy to notice differences. Vegetation grows, ice melts, erosion reshapes landscapes. In the deep ocean, changes are subtle and slow. Without light, there are fewer obvious markers. Sediments shift gradually. Biological communities may change composition without dramatic visual signs. This makes long-term monitoring especially difficult. Instruments must operate autonomously for extended periods, collecting data that will only be interpreted much later. Without visual confirmation, scientists must trust sensors to tell the story. When sensors fail, there may be no backup. Darkness also limits public engagement. Images drive interest and understanding. Photographs of distant galaxies inspire awe. Videos of coral reefs capture attention. The deep ocean offers fewer visually striking scenes. Its beauty is quiet, understated, and often monochromatic. Communicating its significance requires explanation, context, and imagination. This affects funding and support. Projects that produce compelling visuals are easier to promote. Projects that yield graphs, pressure readings, and sparse images struggle to compete for attention. Darkness, in this sense, doesn't just hide the trench from view, it hides it from public consciousness. There is also a philosophical shift that darkness enforces. In well-lit environments, humans tend to dominate. We see, we move, we alter. In darkness, we become guests. Our presence is limited, our understanding partial. We rely on machines and indirect measurements. This fosters a different relationship with the environment, one based more on observation than control. Some scientists find this appealing. The deep ocean resists simplification. It reminds us that not all knowledge is easily acquired or quickly applied. Darkness slows us down, forces us to reconsider assumptions, and exposes the limits of our tools. Others find it frustrating. The lack of immediate feedback, the difficulty of interpretation, and the constant uncertainty can feel like barriers rather than challenges. When resources are limited, it is tempting to focus on environments where progress feels more tangible. All of this feeds into the broader hesitation to go deeper into places like the Mariana Trench. Darkness compounds every other difficulty. It amplifies pressure by making it harder to detect problems early. It increases isolation by limiting communication. It stretches timelines by slowing observation and interpretation. Yet darkness is not just an obstacle. It is also a filter. It reveals which questions are worth pursuing even when answers come slowly. It favours persistence over speed, patience over spectacle. In this way, darkness changes not just the environment, but the nature of exploration itself. As we continue descending into this topic, darkness will remain a constant companion. It will intersect with pressure, with distance, with cost, and with the limits of technology. It will shape not only what scientists can see, but how they think about what they are trying to understand. And in that quiet, unlit space, the trench continues to exist on its own terms, unchanged by whether we look at it or not. Human design is shaped by the environments we evolved in and the problems we needed to solve there. Our tools, machines, and structures carry those assumptions with them, even when we try to push beyond familiar boundaries. On land, we design for gravity pulling downward, for air pressure pushing gently from all sides, for temperatures that fluctuate but rarely kill instantly. Even our most advanced technologies are extensions of these baseline conditions. When we take those designs into the deepest parts of the ocean, Pressure and silence expose just how narrow our comfort zone really is. Pressure has already shown itself as a physical limit, but when paired with silence, it becomes something more subtle and more revealing. Silence in the deep ocean is not merely the absence of sound, it is the absence of feedback. It removes cues that humans and machines rely on to understand their surroundings. Together, pressure and silence form an environment that resists interaction, one that does not announce its dangers loudly or early, but waits patiently for failure. On land, machines often fail gradually. A vibration increases, a sound changes, heat builds up. There are warning signs, small clues that something is going wrong. Engineers learn to listen for them. Drivers recognize the whine of a failing bearing or the rattle of a loose component. These sensory hints allow intervention before catastrophe. In the deep ocean, silence hides these clues. Pressure masks vibration. Thick housings dampen sound. The environment absorbs noise rather than reflecting it back. This means that when something fails at depth, it often fails without warning. A seal gives way, a housing implodes, an electrical short occurs. There is no gradual escalation, no opportunity to respond. The system goes from functioning to destroyed in a fraction of a second. For human designers, this is deeply unsettling because it removes one of the most reliable layers of safety, early detection. To compensate, deep-sea vehicles are designed with extreme conservatism. Redundancy is built in wherever possible. Components are over-engineered. Margins are increased. But every layer of protection adds weight, complexity, and cost. At some point, adding more material stops improving safety and starts introducing new failure modes. A heavier structure requires stronger joints. Stronger joints concentrate stress elsewhere. The design becomes a delicate balancing act. Pressure also imposes strict constraints on shape. Many of the forms humans prefer for vehicles and habitats simply do not work at extreme depth. Windows, flat panels, sharp corners, and modular assemblies all create stress concentrations. Under pressure, these features become liabilities. This is why deep-diving submersibles look so unlike other vehicles. They are compact, rounded, and enclosed, often resembling capsules rather than craft designed for exploration. This shape constraint limits internal space. Crewed vehicles can carry only 1 or 2 people in cramped conditions. Instruments must be packed tightly. Movement is restricted. Comfort is minimal. For short missions, this is tolerable. For extended operations, it becomes exhausting. Humans are adaptable, but there are limits to how long we can function effectively in confined, silent, high-risk environments. Silence amplifies this psychological strain. Inside a deep-sea submersible, sound is muted. There is no wind, no waves, no engine roar. What remains are internal noises, the hum of electronics, the occasional creak as materials adjust under pressure. These sounds are often faint, but they carry disproportionate weight. Every unfamiliar noise becomes a potential threat. Every change invites scrutiny. Outside the vehicle, silence is even more complete. Water transmits sound well over long distances, but in the trench there are few sources. No storms, no surface traffic, no animal choruses. The environment feels static, frozen. This stillness can be disorienting. Humans are accustomed to constant background noise, even if we are not consciously aware of it. Its absence creates a sense of isolation that is difficult to shake. This isolation affects decision-making. In high-risk environments, stress narrows attention. Cognitive load increases. The margin for error shrinks. Deep-sea missions require precise execution under these conditions, often with limited ability to correct mistakes. For crewed missions, this raises ethical and practical questions. How much risk is acceptable? How much stress can be justified in the pursuit of knowledge? These questions are part of why crewed descents into the Mariana Trench are so rare. Unmanned vehicles eliminate risk to human life, but they introduce other limitations. Machines cannot improvise in the same way humans can. They follow programmed instructions. When conditions deviate from expectations, their responses are limited. Pressure and silence magnify this limitation by reducing the flow of information back to operators. Communication between surface ships and deep-sea vehicles relies on acoustic signals. These signals travel slowly and carry limited data. Commands sent from the surface may take seconds or minutes to reach the vehicle. Feedback returns just as slowly. This delay makes real-time control impossible. Operators must anticipate problems rather than react to them. Human-designed systems are often optimized for responsiveness. Pilots adjust controls instantly. Drivers correct course continuously. In the trench, this feedback loop is broken. Designers must accept that once a vehicle descends beyond a certain point, it is effectively on its own. This demands a level of trust in design and programming that is difficult to achieve. Pressure complicates maintenance as well. On land, machines can be inspected, repaired, and modified easily. In space, maintenance is challenging but possible, as astronauts can work outside vehicles in controlled conditions. In the deep ocean, maintenance at depth is nearly impossible. If something breaks, it must either be tolerated or the mission must end. This makes pre-mission preparation critical, and post-mission analysis exhaustive. Every component must be tested, often beyond its rated limits. Even then, uncertainty remains. Materials behave differently under combined stresses. Cold temperatures make some materials brittle. High pressure alters chemical reactions. Long exposure can cause slow deformation. Designers must account for interactions that are difficult to model accurately. Silence also affects how scientists interpret data. Many instruments rely on detecting changes over time. In a dynamic environment, those changes stand out against a noisy background. In the trench, the background is quiet and stable. Signals can be subtle. Distinguishing meaningful variation from sensor drift or noise requires careful calibration and long-term data sets. This makes experimentation harder. On the surface, experiments can be repeated quickly, variables can be adjusted. In the trench, repetition is expensive and slow. Each experiment may represent a once-in-a-decade opportunity. Pressure and silence conspire to make mistakes costly and learning incremental. Human design also struggles with scale in this environment. Many scientific questions require large spatial coverage or long temporal observation. Our tools are either small and mobile or large and stationary. Small vehicles can explore but briefly. Stationary instruments can observe over time, but only in one location. Combining these capabilities under extreme pressure is difficult. Attempts to deploy networks of sensors at depth have met with limited success. Power supply is a major constraint. Batteries must last for years. Energy harvesting is challenging in an environment with little movement or temperature gradient. Cables connecting instruments to the surface are impractical at such depths. Wireless communication is limited by the physics of sound. This forces trade-offs. Instruments may collect less data to conserve power. Sampling rates are reduced. Resolution is sacrificed for longevity. Scientists must decide in advance which measurements matter most, knowing they cannot change their minds easily later. Pressure also limits materials in ways that are not always intuitive. Some materials that perform well under compression fail due to chemical interactions accelerated by pressure. Corrosion behaves differently. Seawater infiltrates microscopic pores. Over time, even well-protected components degrade. This long-term degradation is difficult to study because retrieval itself exposes materials to drastic pressure changes. Silence, meanwhile, limits situational awareness. In noisy environments, humans use sound to detect anomalies. A sudden silence can be as informative as a sudden noise. In the trench, silence is constant. There is no baseline variation to compare against. This removes another layer of intuitive understanding. Designers have tried to compensate by adding more sensors, pressure sensors, strain gauges, acoustic monitors, internal diagnostics. These help, but they also increase complexity. More sensors mean more points of failure, more data to interpret, more potential for false alarms or missed signals. This complexity feeds into hesitation. Each mission becomes a high-stakes test not just of scientific hypotheses, but of engineering philosophy. Simpler designs may be more robust, but they limit capability. More complex designs offer greater functionality, but at the cost of reliability. Pressure and silence punish overconfidence in both directions. Human design also reflects cultural priorities. Exploration programs are influenced by public interest, funding cycles, and institutional memory. Space exploration benefits from decades of sustained investment and a narrative of progress. Deep-sea exploration has been more fragmented. Pressure and silence make it harder to build a compelling story of advancement. Failures in the deep ocean are often invisible. A lost vehicle leaves no wreckage to study easily. No dramatic images circulate. Lessons are learned quietly, within small communities of specialists. This slows collective learning and reinforces caution. Yet, within these constraints, innovation continues. Engineers develop new materials, new pressure-resistant electronics, new sampling methods. Autonomous vehicles become more capable. Data analysis techniques improve. Each advancement pushes the boundaries slightly deeper. Still, the limits remain. Pressure and silence define an environment where human design must be humble. They remind us that not every problem yields to brute force or clever engineering. Some environments require adaptation not just of tools, but of expectations. In the Mariana Trench, this adaptation takes the form of restraint. Scientists choose their missions carefully. They ask specific questions. They accept partial answers. They wait for technology to mature. This is not a failure of imagination, but a recognition of reality. Pressure, silence, and the limits of human design are not separate challenges. They reinforce one another. Pressure destroys, silence conceals, and design struggles to mediate between them. Together, they explain why the deepest parts of the ocean remain among the least explored places on Earth. As we continue this slow descent into understanding, these constraints will keep resurfacing in different forms. They will shape how machines are built, how missions are planned, and how knowledge accumulates. And they will continue to remind us that exploration is not just about how far we can go, but about how carefully we must proceed when the environment offers no forgiveness and no commentary, only wait and quiet. For all the talk of the Mariana Trench as the deepest place on Earth, the number of humans who have actually been there is surprisingly small. Not metaphorically been there, not studied it through data or images or sediment samples, but physically descended to the bottom, sealed inside a vessel, surrounded on all sides by kilometers of water. You can count them on one hand. That fact alone says a great deal about the nature of the place and the choices scientists have made over the decades. The first time a human being reached the bottom of the Mariana Trench was not part of a long, steady program of exploration. It was a singular event driven by a mixture of curiosity, engineering ambition, and Cold War-era confidence that difficult problems could be solved if enough effort was applied. In 1960, the bathyscaphe Trieste carried Jacques Picard and Don Walsh down to what was then believed to be the deepest point of the ocean, Challenger Deep. The Trieste was not a sleek vehicle by modern standards. It looked ungainly, almost improvised, with a large gasoline-filled float for buoyancy and a small steel pressure sphere hanging beneath it. Gasoline was used not as fuel, but because it is less dense than water and incompressible, making it useful for buoyancy at depth. The sphere itself was thick-walled steel, just large enough for two people to sit inside with minimal room to move. The descent took nearly 5 hours. As the Trieste sank deeper, light disappeared, temperature dropped, and pressure climbed relentlessly. Inside the sphere, Picard and Walsh listened to the sounds of the vehicle responding to the environment. At one point, they heard a loud crack, likely caused by an outer window cracking under pressure. The sphere itself remained intact, but the moment underscored how little margin for error existed. When they finally reached the bottom, they stayed there for only about 20 minutes. Visibility was poor. Sediment stirred up by the vehicle created a cloudy haze. They reported seeing what they believed to be a flatfish-like creature, though later interpretations have questioned whether that observation was accurate. Instruments collected basic data, and then, just as deliberately as they had descended, they released ballast and began the long journey back up. That was it. The deepest point on Earth had been reached briefly by two humans, and then, for more than half a century, no one went back. This long gap is often misunderstood. It's tempting to assume that once something has been done, repeating it should be straightforward. In reality, the Trieste mission was a proof of possibility, not a template for routine exploration. It demonstrated that a human could survive the pressure, but it did not demonstrate that doing so was efficient, repeatable, or scientifically productive on a regular basis. The Trieste itself was not well suited for detailed research. It had limited maneuverability, limited instrumentation, and very limited visibility. Its success was as much about endurance as observation. After that first dive, the scientific community faced a decision: invest heavily in building more crewed vehicles capable of reaching such depths, or focus on unmanned systems that could operate without risking human life. Over time, the balance shifted decisively toward unmanned exploration. Remotely operated vehicles and autonomous probes could be sent down more frequently, at lower cost, and without the ethical burden of putting people in harm's way. They could carry cameras, sensors, and sampling equipment. They could fail without loss of life. From a risk management perspective, this made sense, but unmanned exploration comes with trade-offs. Machines do not see the way humans do. They do not improvise intuitively. They do not notice unexpected details unless programmed to look for them. For many scientists, there remained a lingering sense that something was missing, that being physically present at the bottom offered a perspective no instrument could fully replicate. This tension remained unresolved until 2012, when James Cameron made a solo descent to Challenger Deep in the deep-sea Challenger submersible. Unlike the Trieste, this vehicle was purpose-built for a single pilot and designed with modern materials and systems. It was taller and narrower, resembling a vertical torpedo more than a traditional submersible. Cameron's dive was not a government mission. It was privately funded, driven by personal interest and a long-standing fascination with the ocean. He had already spent years working with submersibles and underwater filming technology, particularly during the production of films that required deep-sea footage. This experience gave him both the technical understanding and the motivation to attempt something few others had pursued. The Deep-Sea Challenger incorporated lessons learned from decades of unmanned exploration. It used syntactic foam for buoyancy, a material made of tiny hollow spheres embedded in resin, capable of withstanding extreme pressure. Its pressure hull was smaller than that of the Trieste, reflecting the fact that it carried only one person. This reduced stress and improved safety margins. The descent took about 2.5 hours, significantly faster than the Trieste's journey. Cameron spent roughly 3 hours at the bottom, longer than Picard and Walsh had managed. He collected samples, took high-definition video, and conducted basic observations. Like the earlier dive, visibility was limited by disturbed sediment, but the data collected was more extensive. After Cameron's ascent, there was renewed public interest in the Mariana Trench. Images circulated, interviews were given. The idea of deep-sea exploration briefly re-entered popular conversation, and then, once again, momentum faded. Despite the success of the mission, it did not trigger a wave of new crewed dives. Since then, there have been a few additional crewed descents by specialized vehicles, but the total number of humans who have reached the bottom remains extremely small. Each mission is a major undertaking requiring years of preparation, significant funding, and acceptance of substantial risk. They are not exploratory programs in the traditional sense. They are singular events. This rarity raises an important question. If reaching the bottom is possible, why isn't it done more often? The answer lies in the difference between possibility and practicality. Crewed dives offer unique perspectives, but they are not always the most efficient way to gather data. They are constrained by human endurance, safety requirements, and limited operational time. A human presence also imposes design constraints. Life support systems must function flawlessly. Emergency contingencies must be planned. Psychological factors must be considered. All of this adds complexity and cost. For many research goals, unmanned systems can do the job more effectively. There is also the issue of scientific payoff. The deepest parts of the trench are relatively uniform compared to more dynamic environments, like continental shelves or mid-ocean ridges. While there is certainly life and geological activity, changes occur slowly. A single visit, no matter how carefully conducted, captures only a snapshot. From a scientific planning perspective, repeated unmanned missions that build a long-term data set may offer more value than occasional crewed descents. This does not diminish the importance of the crewed missions that have occurred. Instead, it places them in context. They are milestones, not methods. The people who have touched the bottom often describe the experience in similar terms: isolation, stillness, a sense of being somewhere fundamentally different from the rest of the world. These descriptions are compelling, but they are subjective. Science relies on reproducibility, on measurements that can be repeated and verified. Personal experience, no matter how profound, cannot substitute for systematic data. That said, human presence can shape the direction of inquiry. Observations made during crewed dives have influenced hypotheses and inspired new questions. Seeing the environment firsthand can reveal patterns or anomalies that instruments might overlook. The challenge is translating those insights into research programs that can be sustained without constant human descent. Another factor influencing the rarity of these dives is institutional memory. The Trieste dive occurred in a specific historical context, supported by military resources and Cold War priorities. Cameron's dive occurred in a different context, enabled by private funding and personal motivation. Neither represents a stable, long-term framework for exploration. Without consistent institutional support, crewed deep-sea exploration becomes dependent on individual champions. When those individuals move on, funding dries up, or priorities shift, progress stalls. This pattern has repeated itself multiple times in the history of deep ocean research. There is also an ethical dimension that has become more prominent over time. Risk tolerance has changed. Modern scientific institutions are more cautious about exposing individuals to extreme danger, especially when alternative methods exist. The value of human life is weighed carefully against potential gains in knowledge. This does not mean that crewed exploration is obsolete. It means it must be justified more rigorously. Each proposed dive must answer the question not just of whether it can be done, but whether it should be done, given the costs and risks involved. The few who have touched the bottom of the Mariana Trench occupy a unique place in the history of exploration. They are not pioneers in the sense of opening a new frontier for mass travel. They are more like witnesses, individuals who have briefly entered an environment that remains fundamentally inhospitable to sustained human presence. Their experiences remind us that the deepest parts of the ocean are not empty simply because we have not filled them with activity. They are empty of humans because they resist us at every level, physically, technologically, and institutionally. As we move forward in this exploration, these rare descents serve as reference points rather than endpoints. They show what is possible under exceptional circumstances. They also highlight why those circumstances remain exceptional. The bottom of the Mariana Trench has been touched, but it has not been claimed, settled, or tamed. It remains a place that allows entry only briefly, on strict terms, and with no promise of return visits. and that reality continues to shape how scientists think about going deeper, not just in terms of capability, but in terms of purpose. At first glance, machines seem perfectly suited for the deepest parts of the ocean. They don't need air, they don't feel fear, they don't panic in silence or grow uncomfortable in tight spaces. They can be built to tolerate cold, pressure, and darkness far beyond human limits. On paper, they're ideal explorers for a place like the Mariana Trench. And yet, despite decades of development, increasingly sophisticated engineering, and remarkable successes at shallower depths, machines continue to struggle in ways that reveal an important gap between technical capability and true exploration. The struggle does not come from a lack of intelligence or effort. It comes from the nature of the environment and the kind of curiosity that drives scientific discovery. Machines excel at executing predefined tasks. They follow instructions precisely, repeat measurements reliably, and operate without fatigue. But the deepest ocean is not an environment that rewards rigidity. It is one that constantly presents edge cases, subtle variations, and situations that resist predefinition. Most deep-sea machines are designed around specific goals. Collect sediment here, measure temperature there, map this section of seafloor. These goals are encoded long before the vehicle ever enters the water. Engineers anticipate conditions, program responses, and test systems extensively. But no matter how thorough the preparation, the trench introduces uncertainty that cannot be fully predicted. Seafloor topography can differ from maps by just enough to matter. Sediment can be softer or steeper than expected. Slopes can crumble. Currents can behave differently at depth than models suggest. For a human observer, these deviations might prompt an immediate adjustment, a pause, a closer look, a change in plan. For a machine, deviation is a problem to be managed, not an opportunity to explore. Autonomous underwater vehicles rely on decision trees and thresholds. If this happens, do that. If a sensor reads outside expected bounds, abort or retreat. These safeguards are essential for survival, but they also constrain behavior. Curiosity, as humans experience it, is not efficient. It lingers. It follows anomalies. It tolerates uncertainty. Machines are designed to avoid it. Even remotely operated vehicles which allow human control from the surface face limitations. Communication delays mean that control is never truly direct. Commands arrive seconds later. Feedback returns with equal delay. In a dynamic environment, this lag matters. Operators must anticipate rather than react. Fine adjustments become coarse. Exploration becomes cautious. There is also the issue of perception. Machines perceive the world through sensors, each translating a physical property into data. Pressure sensors measure force. Cameras capture light. Sonar maps distance. Chemical sensors detect composition. Each of these produces a stream of numbers or images that must be interpreted. Humans, by contrast, integrate sensory input instinctively. We notice patterns without consciously analysing them. We recognise when something feels out of place. In the trench, where visual cues are limited and conditions are unfamiliar, this intuitive integration becomes especially valuable. A human might notice an unusual texture in sediment, a subtle change in slope, or a pattern in biological distribution that doesn't fit expectations. A machine will only notice what it has been programmed to notice. This gap is not due to poor design. It reflects a fundamental difference between computation and curiosity. Curiosity is not a single algorithm. It is a layered process shaped by experience, emotion, and context. It involves asking questions that were not anticipated. Machines, no matter how advanced, still operate within the boundaries set by their creators. Machine learning has begun to narrow this gap, but only partially. Algorithms can detect anomalies, classify images, and adapt behavior based on training data. However, training data for the deepest parts of the ocean is scarce. There are a few examples to learn from. Conditions are extreme and variable. Models trained on shallow or mid-depth data may not generalize well to the trench. This scarcity creates a feedback loop. Because machines struggle to explore freely, they collect limited data. Because data is limited, machine learning models remain constrained. Progress is incremental, not transformative. Each mission adds a little more understanding, but rarely enough to redefine what machines can do there. Another challenge lies in physical interaction. Curiosity often involves touch, picking something up, prodding it, breaking it apart to see what's inside. Human hands are extraordinarily versatile. They can apply just the right amount of force, adjust grip instantly, and respond to unexpected resistance. Robotic manipulators are improving, but at depth, their capabilities are restricted. Pressure affects hydraulics and motors. Fine control becomes difficult. A manipulator designed to gently collect a fragile organism may behave unpredictably if pressure alters fluid dynamics or mechanical tolerances. A task that looks simple in a laboratory becomes complex on the seafloor. As a result, machines often err on the side of caution, avoiding interaction unless absolutely necessary. This caution limits discovery. Many deep-sea organisms are delicate. They leave little trace. Without careful handling, they are destroyed or missed entirely. Machines can collect samples, but the process is slow and constrained. Humans, by contrast, can adapt their approach moment by moment, guided by sensory feedback and intuition. There is also the matter of context. Scientific curiosity thrives on context. Observations gain meaning when placed within a broader framework of understanding. Humans are constantly building and revising mental models. When something unexpected appears, it is immediately compared to prior knowledge. Assumptions are questioned, and new hypotheses form. Machines lack this fluid contextual awareness. They process data, but they do not wonder. They do not ask why something is unusual unless instructed to do so. They do not experience surprise. This limits their ability to generate new questions, which is often where the most significant scientific advances begin. In the Mariana Trench, where every observation is rare and valuable, this limitation is especially pronounced. A single unexpected feature could point to an unknown geological process or a new biological adaptation. Recognizing its significance requires not just detection, but interpretation. This is why human involvement remains important, even as machines take on more of the physical burden. Scientists reviewing data from deep-sea missions often notice things that algorithms miss. Patterns emerge only after hours of careful examination. Questions arise that were not part of the original mission plan. However, involving humans more directly comes with costs and risks already discussed. Crewed missions are rare. Remote observation is limited. The result is a compromise. Machines do the exploring. Humans do the interpreting. And between those roles lies a gap where curiosity struggles to fully express itself. The environment itself exacerbates this gap. The trench offers few opportunities for trial and error. Missions are expensive. Failures are final. There is little room for playful experimentation, the kind that often leads to unexpected insights. Machines must perform correctly the first time. This discourages open-ended exploration. In more forgiving environments, curiosity can afford to be inefficient. You can take detours. You can make mistakes. In the trench, inefficiency can mean mission failure. As a result, exploration becomes conservative by necessity. There is also a cultural dimension. Engineering disciplines prioritize reliability, predictability, and control. Scientific curiosity often values flexibility, surprise, and discovery. In extreme environments, engineering constraints tend to dominate. Safety margins take precedence over exploratory freedom. This does not mean machines are failing. They have enabled discoveries that would otherwise be impossible. They have mapped vast areas of the seafloor, revealed unexpected life forms, and expanded our understanding of Earth's extremes. But their struggles highlight a deeper truth about exploration. Exploration is not just about reaching a place, it is about engaging with it. It involves noticing details, asking new questions, and following threads that were not visible at the outset. Machines are excellent at reaching. They are less adept at engaging. As technology advances, this balance may shift. Better sensors, more adaptive algorithms, and improved autonomy will expand what machines can do. But the deepest parts of the ocean will likely continue to test the limits of human design, not because we lack ingenuity, but because the environment resists simplification. Curiosity thrives on ambiguity. The Mariana Trench is full of it. Machines, by their nature, seek to reduce ambiguity. That tension explains why progress there feels slow and careful, rather than bold and sweeping. As we move further along, this tension will remain central. The trench is not just a physical depth, it is a conceptual one, where our tools and our curiosity do not always align. And until they do, machines will continue to struggle in ways that remind us that exploration is as much about how we think as it is about what we build. Every journey into the deepest parts of the ocean carries a quiet question that is never spoken aloud during press briefings or funding announcements, but is always present in planning rooms and engineering reviews. What happens if it doesn't come back? Not the data, not the samples, but the vehicle itself. In the Mariana Trench, this is not a hypothetical concern. It is an expectation that must be planned for, insured against, and ultimately accepted. The cost of going down is easy to describe in numbers. Ships cost money to operate. Crews must be paid. Fuel, logistics, permits, insurance, and months or years of preparation all add up. Specialized submersibles cost tens of millions to design and build. Sensors, cameras, pressure housings, and sampling equipment are custom-made, often one of a kind. Each mission represents an investment large enough to fund entire research programs elsewhere. But the cost of not coming back is harder to quantify and far more influential in shaping decisions. When a deep-sea vehicle is lost, it is not just hardware that disappears. It is years of accumulated knowledge, design lessons, calibration data, and institutional experience. It is momentum. It is confidence. Sometimes it is the end of a research direction entirely. In most fields of science, failure is expected and even welcomed. Experiments fail. Equipment breaks. Hypotheses are disproven. These failures are usually contained. A lab instrument can be repaired or replaced. A field experiment can be repeated. Losses are measured in days or weeks. In the Mariana Trench, failure is absolute. When something goes wrong at 11 kilometers depth, there is no recovery operation. The ocean keeps what it takes. This finality changes behavior. It encourages caution, not because scientists lack bravery, but because they understand the stakes. A lost vehicle can halt progress for years. Funding agencies become hesitant. Engineers are asked to justify every risk. Proposals are scrutinized more harshly. The cost of failure echoes long after the event itself. There are many ways a mission can fail. Pressure housings can implode due to microscopic flaws. Batteries can short-circuit. Software can misinterpret sensor data and make an incorrect decision. Buoyancy systems can malfunction, preventing ascent. Communication links can fail, leaving operators blind and unable to intervene. Any one of these can turn a descent into a one-way trip. What makes these failures particularly challenging is that they often leave little evidence behind. At such depths, implosion happens in milliseconds. Debris is scattered or buried in sediment. There is no black box to retrieve, no wreckage to analyse easily. Engineers are left to infer what went wrong based on indirect clues, test data, and simulation. This uncertainty makes improvement difficult. Learning from failure is a cornerstone of engineering, but it relies on feedback. Without clear information, designers must be conservative, adding safety margins without knowing exactly which failure modes matter most. This increases cost and complexity, which in turn raises the stakes of the next mission. The financial cost of a lost vehicle can be staggering. Some deep-sea submersibles represent investments of decades. They are not mass-produced. Each one is unique, tailored to specific research goals and built by specialized teams. Replacing one is not as simple as ordering another. It may require rebuilding expertise that has dispersed, reassembling teams and restarting supply chains. There is also the opportunity cost. Time spent rebuilding or redesigning is time not spent collecting data. Scientific questions remain unanswered. Students move on, collaborations dissolve. In fast-moving fields, a delay of several years can mean losing relevance or priority. These realities influence how often scientists are willing to attempt extreme depth missions. Even when technology exists, the risk-reward calculation may not favour action. A mission that promises incremental knowledge may not justify the possibility of catastrophic loss. This is not cowardice, it is triage. The cost is not purely financial, there is an emotional toll as well. Engineers and scientists invest deeply in their work. They spend years thinking about a vehicle, anticipating its behaviour, imagining what it might encounter. When it is lost, there is grief alongside frustration. Careers can be affected, confidence shaken. Teams may disband under the weight of disappointment. This emotional dimension is rarely discussed publicly, but it matters. Science is done by people, not abstractions. Repeated losses can make even the most passionate researchers reluctant to push boundaries again. The trench does not just test machines, it tests resolve. Insurance exists, but it cannot replace expertise or lost time. Some missions are partially insured against hardware loss, but insurance premiums reflect risk. At extreme depths, premiums are high if coverage is available at all, and insurance does nothing to address the scientific cost of lost data or disrupted programs. The cost of going down also includes preparation that never sees the light of day. Years of simulations, pressure tests, and design reviews precede a single dive. Many components are tested to destruction. Entire prototypes may be built and discarded. These sunk costs are invisible once the mission begins, but they loom large when considering whether to attempt another descent. There is also the cost to supporting infrastructure. Research vessels capable of supporting deep-sea operations are rare and expensive to operate. Scheduling time on them is competitive. A failed mission ties up resources that could have been used elsewhere. This can strain relationships between institutions and funding bodies. When a vehicle does not come back, questions are asked beyond the technical. Was the mission necessary? Were risks communicated clearly? Could the same goals have been achieved at shallower depths, or through indirect methods? These questions can influence future funding decisions far beyond the immediate project. As a result, scientists often choose alternatives. They study regions adjacent to the trench rather than the deepest point itself. They use sediment cores retrieved indirectly. They rely on modelling and inference. These approaches are safer and cheaper, but they leave gaps in understanding. This does not mean the deepest parts are ignored. It means they are approached sparingly. Each mission must justify itself, not just scientifically, but institutionally. It must promise enough value to outweigh the possibility of total loss. The phrase, "and not coming back," applies not only to vehicles but to data. Even when a submersible returns physically, data can be lost. Storage systems can fail, files can be corrupted, sensors can malfunction. In the trench, redundancy is limited by space and power. Data integrity becomes another vulnerability. To mitigate this, some systems transmit data to the surface during the mission, but acoustic bandwidth is limited. High-resolution video and large datasets cannot be sent in real time. They must be stored on board and retrieved later. If a sent fails, that data is gone forever. This risk shapes mission design. Scientists must choose which data to prioritize, which measurements are essential, which can be sacrificed. These choices influence what questions can be asked and answered. The cost of not coming back also affects collaboration. International partnerships can spread financial risk, but they introduce complexity. Different institutions have different risk tolerances, reporting requirements and expectations. Aligning them around a high-risk mission is difficult. In some cases, private funding steps in, motivated by personal interest or publicity. These missions can be bold, but they are not a substitute for sustained scientific programs. They depend on individual commitment rather than institutional stability. When they end, continuity is lost. All of this contributes to a cautious culture around extreme depth exploration. It is not that scientists lack curiosity. It is that curiosity must operate within constraints. The Mariana Trench demands payment up front, with no guarantee of return. This contrasts sharply with other forms of exploration. In space, failures are public but instructive. Wreckage can be tracked. Telemetry often survives. Lessons are shared widely. In the deep ocean, failures disappear quietly. The trench does not explain itself. There's also a symbolic cost. Each loss reinforces the perception of the trench as an environment that resists human presence. This can shape narratives, making the deep ocean seem forbidding rather than inviting. Narratives influence priorities, and priorities influence funding. Yet despite all this, missions continue. The cost is high, but so is the value of understanding Earth's most extreme environment. The deep ocean plays a role in climate regulation, geological processes, and the limits of life itself. Ignoring it entirely would be a greater loss. The hesitation, then, is not about whether to explore, but how often and how far. Each descent is weighed carefully. Each risk is debated. Each potential failure is imagined in advance. The Mariana Trench has claimed machines, time, money, and patience. It has not been forgiving. But it has also forced science to confront its own limits, to acknowledge that some knowledge comes slowly and at great cost. As we move onward, this reality will continue to shape decisions. The trench does not reward impatience. It does not allow cheap mistakes. Going down is expensive. Not coming back is more expensive still. And between those two facts lies the reason why the deepest place on Earth remains, for now, a place visited rarely, cautiously, and with full awareness of what might be lost when the ocean decides to keep what enters its depth. If you were to design life from scratch, sitting comfortably at the surface with everything we know about biology, the deepest parts of the ocean would not make your short list of viable habitats. No sunlight, near freezing temperatures, crushing pressure, extreme scarcity of food, chemical conditions that would damage cells built for gentler environments. From a surface-based perspective, the Mariana Trench looks less like a place for life and more like a boundary beyond which life should simply give up. And yet, it doesn't. Life exists there. Not in abundance, not in the riot of forms seen in coral reefs or rainforests, but persistently, stubbornly, and in ways that quietly challenge many assumptions about what living systems require. This presence is one of the most compelling reasons scientists remain fascinated by the trench, even as they hesitate to go deeper into it. It is also one of the reasons that exploration there is so difficult to plan, interpret, and justify. The first thing to understand about life at extreme depth is that it does not follow the same rules of visibility as life near the surface. Most organisms in the trench are small, slow-moving, and unobtrusive. They do not announce themselves dramatically. They leave few obvious traces. You do not stumble upon bustling communities or sweeping biological structures. Instead, life reveals itself gradually, often indirectly, through subtle movement, chemical signatures, or the occasional appearance of a creature drifting through a camera's narrow field of view. This subtlety creates an immediate problem for science. Detection is difficult. Absence of evidence is not evidence of absence. But in the trench, absence is the default state of observation. A dive may return hours of footage showing little more than sediment and darkness. That does not mean life is not present. It means it did not intersect with the instruments during that brief window of time. When organisms are encountered, they often defy expectations formed from studying shallower environments. Deep-sea fish may lack swim bladders, as gas-filled organs are useless or dangerous under extreme pressure. Instead, their tissues are adapted to be neutrally buoyant through chemical composition rather than trapped air. Bones may be reduced or flexible, muscles may be gelatinous. Body structures that seem fragile by surface standards are perfectly suited to a world where pressure is uniform and constant. At the cellular level, adaptations are even more striking. Proteins that would normally unfold or malfunction under pressure have evolved structures that remain stable. Enzymes function efficiently at low temperatures and high pressure. Cell membranes are composed differently, maintaining flexibility without leaking or collapsing. These adaptations are not superficial. They are fundamental, woven into the chemistry of life itself. One of the most challenging aspects of studying this life is that many of these adaptations break down the moment the organism is brought to the surface. Pressure drops rapidly, gases expand, cellular processes fail. An organism that functioned perfectly at depth may appear damaged or dead within seconds of retrieval. This makes it extremely difficult to determine how it lived, how it moved, or how it interacted with its environment. As a result, much of what scientists know about trench life comes from indirect evidence. DNA fragments recovered from sediments, chemical signatures indicating metabolic activity, observations of behavior made through brief, artificial illumination. Each piece adds to the picture, but the picture remains incomplete. This incompleteness fuels both curiosity and caution. On one hand, the presence of life where it shouldn't exist raises profound questions. What are the true limits of biology? How flexible is life, really? Could similar forms exist elsewhere, in environments we currently consider hostile? On the other hand, the difficulty of obtaining clear answers makes it hard to build robust theories without over-interpreting sparse data. Food is one of the central mysteries. In the absence of sunlight, life must rely on energy sources that originate elsewhere. The most widespread source is organic material sinking from above, a slow drizzle of dead plankton, waste products, and fragments of larger organisms. By the time this material reaches the trench, it has been filtered, consumed, and decomposed multiple times. What remains is nutritionally poor and unevenly distributed. This scarcity shapes everything. Organisms grow slowly, reproduction may be infrequent, lifespans may be long, energy conservation is paramount. Some trench-dwelling species appear to spend long periods nearly motionless, waiting for rare opportunities. Others have evolved strategies to exploit whatever arrives, no matter how small or infrequent. In some cases, chemical energy supplements this limited supply. In regions influenced by geological activity, chemicals released from the earth can support chemosynthetic bacteria, which form the base of localized food webs. These systems are not common in the trench, but where they exist, they demonstrate that life can decouple itself almost entirely from the surface world. This decoupling is unsettling in the best possible way. It suggests that life is not merely a surface phenomenon dependent on sunlight and mild conditions. It suggests that given enough time and stability, living systems will adapt to exploit almost any consistent energy gradient. For astrobiology, this implication is enormous. It expands the range of environments considered potentially habitable, beyond what was once thought reasonable. But translating that insight into concrete science is difficult. Life in the trench does not behave like a laboratory model organism. You cannot culture it easily. You cannot observe it across generations. You cannot manipulate variables and see immediate responses. Each observation is precious, but isolated. This isolation makes it tempting to romanticize trench life as exotic or extreme. In reality, it is often mundane in appearance, differentiated more by chemistry and physiology than by form. Many trench organisms resemble familiar species from shallower depths, just subtly altered. This resemblance can be misleading. Superficial similarity hides profound internal differences. For scientists, distinguishing between adaptation and coincidence becomes a challenge. Is a trait present because it confers an advantage at depth, or because it happened to persist from an ancestor that lived elsewhere? Without a clear evolutionary history, answers remain provisional. The trench also contains evidence of something else that complicates the picture: human influence. Plastic fragments have been found in trench sediments. Chemical pollutants have been detected in organisms living at depth. These findings are disturbing not because they are surprising, but because they demonstrate how thoroughly human activity has permeated the planet. Life in the trench is not isolated from the surface in the way we once imagined. What happens above eventually reaches below. This adds urgency to understanding these ecosystems, but it also adds ethical complexity. Studying life at depth means interacting with systems that are already under stress, even if that stress is invisible. Another complication is that life in the trench may not be evenly distributed. Some areas may host relatively dense communities, while others are nearly barren. Without extensive sampling, it is impossible to know how representative any single observation is. A dive might encounter several organisms and suggest a thriving ecosystem, or it might encounter none and suggest near emptiness. Both impressions could be misleading. This variability undermines confidence. Scientists prefer patterns they can verify. In the trench, patterns are elusive, the scale is enormous, the access is limited, the data points are sparse. Building models under these conditions requires caution and humility. There is also the question of resilience. Life at depth appears stable over long timescales, but that stability may mask vulnerability. Slow growth and infrequent reproduction mean that recovery from disturbance could take centuries. A single disruptive event, natural or human-caused, might have lasting effects. This possibility makes some scientists hesitant to intervene too aggressively. Sampling disturbs sediments. Lights alter behaviour. Noise travels far. Even the act of observation may carry consequences that are difficult to reverse. When life exists at the edge of energetic viability, even small disruptions can matter. At the same time, avoiding study altogether carries its own risks. Without understanding these ecosystems, we cannot assess their health or vulnerability. We cannot predict how they will respond to changes in climate, chemistry, or human activity. Ignorance is not protection. This tension sits at the heart of deep-sea biology. Life that should not exist does exist, but it exists on terms that challenge how science usually operates. It does not reveal itself easily. It does not conform to expectations. It does not tolerate rapid experimentation. The presence of life in the trench also reframes the meaning of depth itself. Depth is not just a physical measurement, it is a filter. Only certain strategies make it through. Only certain forms persist. What remains is not a random subset of surface life, but a collection shaped by pressure, darkness, and scarcity over immense spans of time. For scientists, this means that every organism encountered is a result of extreme selection. Studying them is like reading a record of what biology can become when pushed to its limits. But reading that record requires tools, patience, and methods that are still evolving. The difficulty of studying trench life feeds back into the broader hesitation to go deeper. Each mission promises insight, but not certainty. Discoveries are incremental. Breakthroughs are rare. For institutions balancing many priorities, this makes investment harder to justify. And yet, the questions refuse to disappear. If life exists here, where else might it exist? What does this tell us about the origins of life on Earth? How does it change our understanding of habitability beyond our planet? These are not small questions, they are foundational. The Mariana Trench forces science to confront a reality that is both inspiring and frustrating. Life is more adaptable than we imagined, but less accessible than we would like. It thrives where it should not, but it does so quietly without spectacle, demanding careful attention rather than bold intrusion. As this exploration continues, life in the trench remains one of its most compelling mysteries, not because it is abundant or dramatic, but because it exists at all. In a place defined by pressure, darkness and silence, life persists, reshaped by conditions that push biology to its outer edge. And in doing so, it reminds us that the limits we perceive are often limits of our tools, our patience and our perspective, rather than limits of life itself. In most environments humans explore, communication is assumed. It is not treated as a luxury or a challenge, but as a baseline condition. Voices travel through air. Radio waves move effortlessly across open space. Signals bounce, repeat, and return. Even when distances are vast, there is usually a dependable way to stay connected. In the Mariana Trench, that assumption collapses. Sound behaves strangely. Signals weaken, distort, and disappear. The deeper you go, the less the environment is willing to carry information back with you. Water is often described as an excellent medium for sound, and in many ways it is. Sound travels faster in water than in air, and over long distances it can propagate efficiently. Whales communicate across entire ocean basins. Submarines rely on sonar to navigate and detect objects far beyond visual range. But this apparent advantage hides complexity. Sound does not travel uniformly through the ocean. It bends, refracts, scatters, and fades depending on pressure, temperature, salinity, and depth. In the trench, all of these factors converge in ways that complicate communication. Temperature is nearly uniform and close to freezing. Pressure is extreme and constant. Water density changes subtly with depth. These conditions create layers that affect how sound waves move. Some frequencies travel farther than others. Some are absorbed. Some scatter unpredictably. What works well at one depth may fail completely at another. For deep-sea vehicles, communication relies almost entirely on acoustics. Radio waves, which form the backbone of modern communication on land and in space, do not travel far in seawater. They are absorbed quickly, reduced to nothing within meters. Optical communication is equally impractical. Light scatters and fades rapidly, especially in water filled with particles and sediment. That leaves sound as the only viable option. Acoustic communication, however, is slow. Sound travels through water at roughly 1,500 meters per second, which is fast compared to air but slow compared to the speed of light. At trench depths, signals can take several seconds to travel between a vehicle and a surface ship. That delay may not sound significant, but it fundamentally alters how systems are controlled. Real-time communication becomes impossible. A command sent from the surface reaches the vehicle after a noticeable pause. The vehicle's response takes just as long to return. In complex or dynamic situations, this lag matters. By the time operators see what has happened, the moment has already passed. Adjustments must be anticipatory rather than reactive. Bandwidth is another limitation. Acoustic signals can carry only limited amounts of data. High-resolution video, detailed sensor streams, and complex telemetry cannot be transmitted in real time. Vehicles must store most of their data on board, hoping to return safely so it can be retrieved later. This creates a constant tension between what scientists would like to know immediately and what the environment allows them to know only after the fact. The trench does not merely slow signals, it degrades them. Acoustic communication is vulnerable to interference from the environment itself. Small changes in water conditions can alter signal paths. Reflections off the seafloor can distort messages. Noise from the vehicle's own movement can mask incoming signals. Even biological activity, though sparse, can contribute to background noise. Silence in this context is deceptive. The trench feels quiet because there are few obvious sound sources, but that does not mean it is acoustically simple. The absence of noise does not guarantee clarity. Instead, it removes reference points. When a signal weakens or changes, it is difficult to determine whether the cause is distance, interference, equipment malfunction, or environmental variation. This uncertainty makes communication fragile. Engineers must design systems that tolerate partial information, missed packets, and ambiguous feedback. Commands are simplified. Redundancy is added where possible. But redundancy consumes power, and power is limited. Every choice becomes a trade-off. The trench also swallows signals physically. Depth increases the distance sound must travel. A vehicle at the bottom of the Mariana Trench may be nearly 11 kilometers below the surface, and the acoustic path may not be straight. Sound waves curve as they move through layers of differing density. This can lengthen the effective distance and weaken the signal further. In some cases, communication is lost entirely for portions of a dive. Vehicles operate in near isolation, executing pre-programmed tasks without contact. Operators wait, listening for the faint return of a signal, uncertain whether silence means success, delay, or failure. This waiting is a defining feature of deep-sea exploration. It demands patience and restraint. Navigation suffers alongside communication. GPS signals do not penetrate water. Position must be inferred using inertial systems, sonar mapping, and occasional acoustic fixes from the surface. Errors accumulate over time. A small drift can grow into a significant positional uncertainty. In the trench, where visual landmarks are scarce, correcting these errors is difficult. This positional uncertainty complicates science. Knowing exactly where a sample was collected matters. Geological context depends on precise location. Biological distributions cannot be mapped accurately without reliable positioning. When signals are weak or intermittent, this precision erodes. The trench also affects how signals behave vertically. Sound travelling upward toward the surface may encounter layers that reflect or refract it back downward. This creates acoustic shadows, regions where communication is unexpectedly poor. These effects are difficult to predict and vary with conditions. A channel that worked on one dive may fail on the next. For scientists accustomed to environments where communication is constant and dependable, this is deeply uncomfortable. It forces a shift in mindset. You must accept that you will not always know what is happening. You must design missions that can tolerate long periods of silence. You must trust machines to behave as expected in your absence. Trust, in this context, is not emotional. It is technical. It is built through testing, simulation, and incremental progress. But no amount of preparation can eliminate uncertainty entirely. The trench ensures that something will always be unknown. This swallowing of signals has broader implications. It limits collaboration during missions. Specialists cannot all weigh in simultaneously. Decisions must be made by small teams, often with incomplete information. Opportunities to adjust experiments on the fly are rare. Once a vehicle descends past a certain point, the plan is largely fixed. This rigidity contrasts with exploration in more accessible environments. On land, field researchers adapt continuously. In space, mission controllers adjust trajectories and operations based on real-time telemetry. In the trench, flexibility is constrained by physics. Sound also behaves differently near the seafloor. Soft sediments absorb acoustic energy, reducing reflections. This makes sonar mapping less effective in some areas. Hard surfaces reflect sound strongly, creating echoes that can confuse interpretation. Distinguishing between geological features and acoustic artifacts requires experience and careful analysis. These challenges extend to passive listening as well. Seismometers and hydrophones placed at depth must operate autonomously, recording data over long periods. Retrieving that data requires the instrument to detach from the seafloor and float back to the surface. If the release mechanism fails, the data is lost. If the instrument drifts, recovery becomes difficult. Once again, the cost of silence is finality. Lost signals mean lost information. There is no backup copy stored somewhere else. The trench does not archive what passes through it. This has influenced how scientists frame their questions. Research in the trench often focuses on measurements that can tolerate gaps, long-term averages, rare events captured opportunistically, broad patterns rather than fine-grained dynamics. Questions that require continuous monitoring or immediate response are avoided. This does not mean such questions are unimportant. It means the environment is not yet ready to answer them reliably. Technology may improve, but physics sets limits that cannot be engineered away entirely. The swallowing of sound and signals also affects public perception. The deep ocean feels inaccessible because it is. Communication delays and data gaps make live broadcasts impractical. There are no continuous feeds, no moment-to-moment updates. Exploration unfolds quietly, reported only after the fact. In a media landscape accustomed to immediacy, this quietness can be mistaken for inactivity. In reality, it reflects a different tempo, one imposed by the environment rather than by human preference. The trench teaches patience. It demands that scientists accept silence as part of the process, not as failure, but as a condition of engagement. Information comes slowly, sometimes reluctantly. Signals arrive faint and incomplete. Meaning must be assembled piece by piece. As we continue deeper into this discussion, the swallowing of sound and signals will echo through other challenges. It reinforces isolation. It amplifies risk. It constrains design. It shapes what kinds of questions can be asked and how confidently they can be answered. In the Mariana Trench, communication is not a given. It is a fragile thread stretched across immense depth, and at any moment that thread can thin, fade, or break, leaving explorers alone with their machines, their assumptions, and the quiet pressure of a world that does not speak unless it chooses to. When people hear the phrase "the Mariana Trench hides," the instinct is to imagine secrets in the dramatic sense. Unknown creatures, lost worlds, something spectacular waiting just out of sight. That expectation says more about human storytelling than about the trench itself. What the Mariana Trench hides from us is not a single revelation or a neatly packaged mystery. It hides complexity, slowness, subtlety, and processes that do not announce themselves clearly or all at once. The hiding begins with access. The trench is not hidden because it is invisible. We know where it is. We have mapped its broad shape. We know its depth to within a small margin of error. What makes it hidden is that almost everything meaningful about it happens beyond our ability to observe continuously. Each visit is brief. Each measurement is partial. Between those moments, the trench continues doing whatever it does, uninterrupted and unrecorded. This intermittent access shapes all understanding. Imagine trying to understand a city by visiting it once every few decades, at night, with a flashlight that only illuminates a few meters ahead. You might learn the street layout. You might notice a few buildings. You might see people pass by. But you would miss the rhythms, the patterns, the cause and effect relationships that only become visible through sustained presence. The Mariana Trench exists in that gap. One of the first things it hides is change. On the surface, change is obvious. Weather shifts. Plants grow. Animals migrate. Human activity leaves marks everywhere. In the trench, change happens slowly and quietly. Sediments accumulate grain by grain. Chemical reactions proceed over centuries. Geological forces act with patience measured in millions of years. Without long-term observation, these changes are almost invisible. This slowness is deceptive. It can create the illusion of stability, as if the trench is static and unchanging. In reality, it is dynamic, but on timescales that do not align with human attention spans or funding cycles. Tectonic plates continue to move. Earthquakes occur, slopes collapse. Organic material arrives unevenly. Life responds gradually. The trench is active, but its activity does not perform for observers. Another thing the trench hides is context. Data collected at depth often lacks the surrounding information needed to interpret it fully. A temperature reading tells you what the temperature was at that moment, but not how it varies over time. A sediment sample reveals composition, but not how it arrived there or how it might change. A biological observation shows an organism, but not its population, dynamics, or interactions. Context requires continuity, and continuity is difficult at extreme depth. Instruments deployed for long periods must survive pressure, corrosion, and power constraints. Many fail before they can tell a complete story. Those that succeed return limited data, shaped by design choices made long before deployment. The trench hides the rest. There is also the matter of scale. The Mariana Trench is not a single point. It is a vast, complex system extending thousands of kilometers. Conditions vary along its length. Depth changes. Geology shifts. Biological communities differ. When we speak about the trench as if it were one place, we flatten that complexity. This flattening hides variability. A sample collected at one location cannot represent the whole. An observation made on one dive cannot be generalized confidently. Patterns may exist, but they are difficult to confirm without extensive coverage. The trench hides these patterns simply by being too large and too inaccessible to survey comprehensively. Technology contributes to this concealment as well. Every instrument has limits. Cameras show only what light reveals. Sonar abstracts reality into shapes and distances. Chemical sensors measure specific compounds while ignoring others. What we detect is shaped by what we choose to look for. This selective visibility means the trench hides anything that falls outside our current questions. Processes we have not thought to measure remain unseen. Organisms that do not interact with our instruments go unnoticed. Phenomena that do not produce clear signals remain undetected. The trench does not hide actively. It hides passively by exceeding our curiosity's current boundaries. There is also a biological subtlety that resists easy detection. Many trench organisms are small, sparse, and slow. They do not form dense populations. They do not move frequently. They do not produce dramatic effects. Life may be present in ways that are statistically invisible over short observation periods. This creates uncertainty. Is a lack of observation evidence of absence, or simply a reflection of limited sampling? Without repeated long-term data, it is difficult to answer. The trench hides abundance by spreading it thinly across space and time. Geologically, the trench hides processes that are central to the planet's evolution. Subduction zones recycle Earth's crust, driving volcanism, earthquakes, and the long-term cycling of materials. The Mariana Trench is part of this system, yet much of what happens there occurs deep beneath sediments and rock, far below even the trench floor. We infer these processes through indirect measurements, seismic waves, chemical signatures, modelling. But inference is not observation. The trench hides the details, the exact mechanics of how plates interact, how fluids move, how energy dissipates. These hidden processes matter, but they unfold out of reach. The trench also hides history. Sediments at the bottom accumulate records of past events, volcanic ash layers, chemical anomalies, traces of ancient climate shifts. In theory, these sediments are archives. In practice, accessing them is extremely difficult. Drilling at such depths poses enormous technical challenges. Cores retrieved are short, fragmented, and rare. As a result, much of Earth's history stored in the trench remains unread. We know it is there, but we cannot access it easily enough to integrate it fully into our understanding of planetary change. The trench hides time itself, compressed into layers that are frustratingly difficult to reach. Human influence is hidden there too. Pollutants sink, plastics fragment and settle, chemical residues travel downward. Their presence in the trench reveals how interconnected the planet is, but it also hides scale. We detect contamination, but we do not yet understand its distribution, concentration, or long-term effects on deep-sea ecosystems. This lack of understanding complicates responsibility. It is easier to address problems we can see clearly. The trench hides damage by making it diffuse and remote. That remoteness can delay action, not out of malice, but out of uncertainty. Another layer of concealment comes from interpretation itself. Scientists are cautious, as they should be. Sparse data demands careful analysis. Claims must be restrained. This restraint can make discoveries feel less dramatic than they are. Important findings are often framed tentatively, buried in technical language and understood fully only by specialists. To the outside world, this can look like a lack of progress. In reality, it reflects the difficulty of extracting reliable meaning from limited observations. The trench hides clarity, forcing science to proceed slowly and conservatively. There is also a philosophical dimension to what is hidden. Humans tend to think of exploration as a process of uncovering, of revealing what was previously unknown. The Mariana Trench challenges this narrative. It suggests that some environments do not yield their secrets easily, not because they are hostile, but because they operate on different terms. The trench does not offer dramatic revelations on demand. It does not reward brief visits with comprehensive understanding. It requires sustained engagement that we're not yet equipped to provide. In this sense, it hides, not because it is secretive, but because we are impatient. Even when we do see something unexpected, the trench hides explanation. An unusual organism appears on camera. A chemical anomaly is detected. A geological feature does not fit existing models. These moments generate questions, not answers. Without follow-up, they remain curiosities rather than insights. Follow-up, however, is expensive and risky. Returning to the same location may take years. Conditions may have changed. The original phenomenon may not reappear. The trench hides repeatability, a cornerstone of scientific confidence. This leads to a kind of asymmetry. The trench can surprise us easily, but it is hard for us to surprise it back with understanding. It absorbs attention without offering closure. For some scientists, this is deeply motivating. For others, it is discouraging. What the Mariana Trench hides most effectively is simplicity. There is no single reason why it remains poorly understood. There is no single barrier to exploration. Instead, there is a layering of obstacles that interact in subtle ways. Pressure limits time. Darkness limits perception. Distance limits communication. Cost limits repetition. Each limitation reinforces the others. This layering means that even as individual challenges are addressed, the overall difficulty remains. Improved materials and communication still lags. Improve sensors and deployment remains risky. Improve autonomy and interpretation still requires human judgment. The trench hides behind the sum of its parts. It also hides opportunity cost. Every mission to the deepest point diverts resources from other research. Those decisions are not made lightly. Scientists must choose where to focus attention, knowing that no choice is neutral. The trench hides itself partly by being one option among many, competing for limited time and funding. And yet, despite all this, the trench continues to draw interest. Not because it promises easy answers, but because it exposes the limits of our knowledge in a way few other places do. It hides things that matter, even if we cannot yet articulate exactly how. In hiding so much, the Mariana Trench serves as a mirror. It reflects the boundaries of our technology, our patience, and our scientific culture. It shows where our tools fall short and where our questions outpace our methods. As this exploration moves forward, what the trench hides will continue to shape how scientists approach it. Not as a puzzle to be solved quickly, but as a system to be approached gradually, with humility and restraint. The Mariana Trench does not conceal its secrets out of malice or mystery. It conceals them because it exists on scales of depth, time, and complexity that do not align with human convenience. And until our methods evolve to meet those scales, much of what happens there will remain hidden, not forever, but for now, quietly unfolding beyond our reach. At first, the idea sounds backwards. Space is vast, cold, airless, and filled with radiation. The deep ocean is right here on Earth, wrapped in familiar water, beneath a sky we know well. One feels alien and extreme, the other feels adjacent, almost domestic. And yet, when scientists and engineers talk candidly about exploration, many will tell you the same thing. In practical terms, space is easier than the deep ocean. Not safer in every respect, not simpler in theory, but easier to work in, easier to design for, and easier to sustain as a long-term scientific effort. This is not an insult to space exploration, nor is it a dismissal of its dangers. It is a recognition of how environments interact with technology and human systems. Space is hostile, but it is consistently hostile. The deep ocean is hostile in ways that are layered, compressive, corrosive, and relentlessly unforgiving to small mistakes. One of the most important differences is pressure, or rather, the lack of it. In space, the dominant challenge is vacuum. There is almost no external pressure at all. That creates problems, but they are problems engineers have learned to manage. Structures want to push outward, not inward. Seals are designed to keep air in rather than keep crushing force out. Materials behave predictably when there is little resistance around them. In the deep ocean, pressure is omnipresent and increasing. It does not pull things apart, it squeezes them inward from every direction. This inversion matters enormously. Engineering for outward pressure allows for redundancy and gradual failure. Engineering against inward pressure allows for neither. When something gives way at depth, it does not leak gently, it collapses violently. This single difference shapes nearly every other comparison. Spacecraft can be large, modular, and assembled from multiple components. They can have flat surfaces, windows, extended arms, and delicate instruments exposed to the environment. Deep-sea vehicles must be compact, rounded, and sealed. Anything that creates a stress concentration becomes a risk. Maintenance is another stark contrast. In space, maintenance is difficult, but it is possible. Astronauts can perform spacewalks. Robots can be sent to repair satellites. Components can be swapped, upgraded, or reinforced. In low Earth orbit, the International Space Station has been continuously inhabited and maintained for decades. In the deep ocean, there is no equivalent. There are no underwater stations at trench depth. There are no repair missions once a vehicle is deployed. If something fails, the mission ends. If something breaks catastrophically, the vehicle is lost. This lack of maintainability forces designs to be conservative and missions to be short. Communication further tilts the balance. In space, communication relies on radio waves travelling at the speed of light. Even with delays across vast distances, bandwidth is high and signals are stable. Engineers can receive detailed telemetry, high-resolution images, and live video feeds. Commands can be sent with precision. Problems can be diagnosed in real time. In the deep ocean, communication crawls. Acoustic signals are slow, limited, and fragile. Bandwidth is scarce. Real-time control is impossible. Much of what happens during a dive remains unknown until the vehicle returns, assuming it does return. This isolation forces autonomy, but autonomy without feedback is inherently risky. Navigation follows a similar pattern. In space, position can be determined precisely using stars, inertial systems, and tracking from Earth. Orbits are predictable. Motion follows well-understood physics. Small adjustments can be calculated and executed accurately. Underwater, especially at extreme depth, navigation is approximate. GPS signals do not penetrate water. Position must be inferred indirectly. Errors accumulate. Currents introduce uncertainty. The seafloor provides few landmarks. Knowing exactly where you are, relative to previous observations, is a persistent challenge. Thermal conditions also favour space in unexpected ways. Space is cold, but it is predictably cold. Thermal management systems are designed to radiate heat away or retain it as needed. Temperature changes can be modelled accurately based on exposure to sunlight and shadow. The deep ocean is cold as well, but the combination of cold and pressure alters material behaviour in more complex ways. Lubricants thicken. Metals become brittle. Electronics behave differently. Corrosion accelerates. Salt water infiltrates microscopic imperfections. These effects compound over time and are difficult to simulate fully on land. Then there is visibility. Space is dark, but it is optically clear. When you shine a light or look toward a star, there is little interference. Cameras perform well. Images are sharp. Distance is vast, but clarity is high. In the deep ocean, darkness is combined with scattering. Light reflects off particles, sediments, and organisms. Visibility is often limited to a few meters. Artificial lighting disturbs the environment and creates glare. Cameras struggle to capture context. What you see is a narrow slice of reality surrounded by blackness. This affects both science and storytelling. Space exploration produces images that are immediately compelling. Planets, moons, nebulae. Even abstract data can be visualized in ways that resonate with the public. The deep ocean produces images that require explanation and patience. A patch of sediment, a slow-moving creature, a faint chemical gradient. These are important, but they do not speak for themselves. Public engagement matters because it influences funding and continuity. Space exploration has benefited from sustained political and cultural support. It has clear milestones, launches, orbits, landings. Progress is visible and cumulative. Deep-sea exploration has been more episodic. Missions occur irregularly. Vehicles are retired or lost. Programs start and stop. Knowledge accumulates, but slowly and unevenly. This inconsistency makes long-term planning difficult. There is also the question of scale and payoff. Space missions often answer questions that are cleanly defined. Measure atmospheric composition, map surface features, detect radiation. Results can be compared across missions and targets. In the deep ocean, questions are often more entangled. Biology, chemistry, and geology interact in complex ways. Isolating variables is hard. Answers are provisional. Risk perception plays a role as well. Space is perceived as dangerous, but its dangers are well publicized and in some sense accepted. There is a long history of managing risk through redundancy, testing, and incremental progress. Failures are visible, analysed, and learned from. Deep-sea failures are quieter. Vehicles vanish. Causes are inferred rather than observed. Lessons are harder to extract. This quietness does not inspire confidence, even when the underlying risk is comparable. Another subtle difference lies in gravity. In space, microgravity simplifies some aspects of design. Structures do not need to support their own weight. Loads are reduced. Movement requires less energy. In the deep ocean, gravity remains fully present, compounded by buoyancy and drag. Vehicles must fight resistance constantly. Motion is slow and energy-intensive. Energy itself is easier to manage in space. Solar power is abundant and reliable near Earth. Batteries can be recharged. Nuclear sources can provide long-term power. In the deep ocean, sunlight is unavailable. Energy must be carried on board. Batteries limit mission duration. Energy harvesting is minimal. Every action consumes a finite resource. Time also behaves differently. Space missions can operate for years or decades. Probes travel far beyond their original targets, continuing to send data. Satellites circle Earth endlessly. Longevity is built into mission design. Deep-sea missions are brief by necessity. Hours or days at depth, then return. Long-term instruments are deployed, but they're passive and limited. Active exploration cannot be sustained continuously. All of this leads to a counterintuitive conclusion. Space is extreme, but it is an environment we can negotiate. The deep ocean is familiar, but it resists negotiation. Space allows us to bring our assumptions with us. The trench forces us to abandon them. This does not mean space is easy. It means it is compatible with how human technology evolved. Radio communication, modular construction, maintenance, and visualization all align naturally with space. They clash with the realities of extreme depth. There is also a psychological factor. Space offers perspective, views of Earth, a sense of expansion. Even isolation feels expansive. The deep ocean offers confinement, darkness, compression. The human mind responds differently to these conditions, and that response influences how willing we are to invest effort and risk. For scientists, this difference translates into strategic choices. If a research question can be answered in space or at depth, space often wins. Not because it is less interesting, but because it is more tractable, more repeatable, more communicative. The irony is that the deep ocean is closer, older, and arguably more relevant to Earth's systems than many space targets. It plays a direct role in climate, geology, and the limits of life. But relevance does not equal accessibility. When engineers say space is easier, they are not diminishing the achievement of space exploration. They are acknowledging a mismatch between our tools and the deep ocean's demands. Space challenges us intellectually and technically. The trench challenges us structurally, logistically, and institutionally. This mismatch explains why, despite centuries of maritime history, the deepest parts of the ocean remain less explored than the surfaces of distant worlds. It explains why we have better maps of Mars than of much of our own seafloor. It explains why progress in the trench feels tentative rather than triumphant. As technology evolves, some of these gaps may narrow. Better materials, improved autonomy, new energy sources, and smarter sensing may make the deep ocean more accessible. But physics will not change. Pressure will remain. Darkness will remain. Communication limits will remain. Space, by contrast, will continue to offer an environment where our tools can stretch rather than buckle, where failure can be analysed and learned from, where exploration can build momentum instead of resetting after each loss. So when scientists say space is easier than the deep ocean, they are not making a poetic comparison. They are stating a practical truth. One environment bends to our methods, the other demands that we change them entirely. And until we do, the deepest parts of the ocean will remain places we visit rarely, carefully, and with an understanding that the greatest barrier is not distance, but the way Earth itself resists being known at its deepest point. Science has a reputation for confidence, white lab coats, precise instruments, clear answers delivered with charts and equations. But behind that public image lies something quieter and far more cautious. Scientists are often less afraid of not knowing than they are of knowing too quickly. In places like the Mariana Trench, this caution becomes especially pronounced. The questions are big, the data is thin, and the consequences of premature conclusions can ripple far beyond a single paper or expedition. When scientists hesitate to answer certain questions about the trench, it is not because they lack hypotheses, it is because the environment punishes overconfidence. The deeper you go, the more every assumption is tested, and the more dangerous it becomes to mistake a partial picture for a complete one. One of the most sensitive questions concerns limits. How deep can life really exist? It is tempting to answer this definitively, to draw a line on a chart and declare everything below it lifeless. But history has shown how often such lines move. Time and again, organisms have been discovered thriving in conditions once thought impossible. High pressure, extreme cold, toxic chemistry. Each discovery forces a reassessment, not just of biology, but of how confidently we draw boundaries. In the Mariana Trench, life exists near the deepest known point, but how representative is that observation? Does life persist everywhere at that depth, or only in specific microenvironments? Are we seeing a stable ecosystem, or the remnants of one slowly declining? With so few data points, any answer risks being misleading. Scientists know this, and so they resist final statements. Another question that invites caution is how fragile these deep ecosystems really are. There is growing concern about human impact reaching even the deepest parts of the ocean. Pollutants sink, plastics fragment, chemical residues travel downward. When traces of these materials are found in trench organisms, the instinct is to sound alarms. But without understanding baseline conditions, scale, and variability, it is difficult to assess impact accurately. Is the presence of contaminants evidence of harm, or simply evidence of connectivity? Are these ecosystems resilient to low-level disturbance, or are they vulnerable in ways we cannot yet measure? Answering too quickly risks either complacency or unnecessary panic. Both can distort policy and public perception. Then there is the question of geological risk. The Mariana Trench sits at a major subduction zone, where tectonic plates collide and one sinks beneath another. This process drives earthquakes and tsunamis. Understanding it matters not just for curiosity but for hazard assessment. Yet the mechanics of subduction at extreme depth remain poorly constrained. Scientists can model these processes, but models rely on assumptions. Direct observation is limited. Instruments provide snapshots, not continuous records. Declaring certainty where uncertainty remains could lead to flawed risk estimates, with real-world consequences for coastal communities. There are also questions about climate. The deep ocean plays a role in carbon storage and heat distribution. It absorbs vast amounts of carbon dioxide and excess heat from the atmosphere. But how much of this process involves the deepest trenches? How stable is that storage? Could changes in circulation or chemistry alter it over time? These questions intersect with global climate policy. Overstating the trench's role could lead to false reassurance. Understating it could obscure important feedbacks. Scientists tread carefully here, aware that their words may be interpreted far beyond their intended scope. Even seemingly straightforward questions invite hesitation. How old is the life at the bottom of the trench? Did it evolve there, or migrate from shallower depths? How isolated are these populations genetically? Answering these requires genetic data, evolutionary models, and assumptions about dispersal that are difficult to verify. Sampling bias looms large. A few specimens cannot represent an entire ecosystem. Genetic signals may reflect recent arrivals rather than ancient lineages. Drawing conclusions too quickly risks rewriting evolutionary history based on incomplete evidence. There is also the question of uniqueness. Are trench ecosystems fundamentally different from other deep-sea environments? Or are they variations on a broader theme? This matters because it shapes how we prioritize research. If the trench is unique, it demands focused attention. If it is representative, studying other deep environments may suffice. The temptation to declare uniqueness is strong. Extreme environments make for compelling narratives, but scientists know that uniqueness must be demonstrated, not assumed. Overemphasizing difference can isolate research fields and limit integration with broader understanding. Another sensitive question concerns technology itself. How close are we to overcoming the barriers of depth? It is easy to frame technological progress as inevitable, a steady march toward greater capability. But the trench challenges that narrative. Some barriers are not just technical, but physical. Pressure, communication limits, and energy constraints may never be fully eliminated. Admitting this is uncomfortable. It runs counter to the idea that science can solve any problem given enough time and funding. Scientists must balance optimism with realism, knowing that overstating feasibility can lead to misallocated resources and disappointment. There are also ethical questions that scientists are cautious to answer definitively. Should we be exploring the deepest parts of the ocean more aggressively? Does the potential knowledge gained justify the disturbance caused? How do we weigh curiosity against conservation when the impacts are uncertain? These are not questions science can answer alone. They involve values, priorities, and risk tolerance. Scientists can inform the discussion, but they are wary of presenting their views as objective conclusions. Answering too quickly risks stepping beyond evidence into advocacy, which can undermine trust. The question of human presence is particularly fraught. Should humans be descending to the trench at all, or should exploration be left entirely to machines? Crewed missions offer unique perspectives, but they carry risk and cost. Declaring one approach superior requires value judgments as much as technical analysis. There is also the issue of narrative. The public often wants clear answers. Is the trench dangerous? Is it fragile? Is it full of life? Is it worth exploring? Scientists know that honest answers are often conditional. It depends on location, on timescale, on what you mean by dangerous or fragile or full. Resisting the pressure to simplify is itself an act of integrity. It means accepting that uncertainty is not a failure, but a reflection of reality. In extreme environments, uncertainty is not a temporary state on the way to clarity. It is a persistent feature. Scientists are also aware of history. Many past claims about the deep ocean were wrong. Assumptions about lifeless depths, uniform conditions, and static environments have all been overturned. This history encourages humility. It warns against declaring that we now finally understand. There is a professional dimension to this caution as well. Scientific credibility depends on reproducibility and robustness. In the trench, reproducibility is hard, missions are rare, conditions vary, datasets are small. Publishing bold conclusions based on limited evidence risks later retraction or revision. Such revisions are part of science, but in high-profile areas they can be damaging. They can erode public trust and fuel skepticism. Scientists working on the trench are acutely aware of this, and so they frame conclusions carefully, often emphasizing limitations more than results. The questions scientists are afraid to answer too quickly are often the most important ones. They touch on limits, risks, and implications that extend beyond a single discipline. They connect the trench to broader debates about life, climate, technology, and responsibility. This caution can be misinterpreted as reluctance or lack of ambition. In reality, it reflects respect for complexity. The trench does not offer simple answers, and pretending otherwise would do more harm than good. There is also an internal tension between curiosity and restraint. Scientists are driven by the desire to know, but they are also trained to doubt, to test, to withhold judgment until evidence accumulates. In the Mariana Trench, these impulses are in constant negotiation. Curiosity asks, what if? Restraint asks, what if we're wrong? Both are necessary. The fear is not of the answer itself, but of answering before the question has been fully earned. As exploration continues, some of these questions will become clearer. Data will accumulate, models will improve, confidence will grow, but it will grow slowly, unevenly, and with frequent reassessment. The trench teaches a particular kind of scientific patience. It forces researchers to live with unanswered questions longer than they might like. It rewards those willing to sit with ambiguity rather than rush to resolution. In that sense, the Mariana Trench is not just a physical depth. It is an intellectual one. It challenges not only our tools, but our habits of thought. It asks whether we can accept uncertainty without filling it prematurely. The questions scientists are afraid to answer too quickly are not signs of weakness. They are signs of maturity. They reflect an understanding that in the deepest places on Earth, knowledge does not arrive fully formed. It accumulates slowly, shaped by caution, humility, and the recognition that some answers, when forced too early, can obscure more than they reveal. And so, for now, many of the most important questions remain open. Not because they cannot be answered, but because answering them responsibly requires more time, more data, and a willingness to let the trench remain, at least for a while longer, only partially understood. When people think about unexplored places, they often imagine blank spaces on old maps, edges of continents marked with uncertainty, or distant planets waiting for first contact. The idea of the unknown is usually framed as something far away. But the depths we leave unexplored are not distant at all. They are directly beneath us, separated not by light years, but by water, pressure, and a set of choices we keep making, consciously and unconsciously. The Mariana Trench is not unexplored because it is invisible. It is unexplored because it demands more than curiosity alone. It demands patience, restraint, and an acceptance that progress there will never look like progress elsewhere. No steady stream of discoveries, no dramatic milestones every few years, no clear finish line where understanding suddenly clicks into place. Instead, there is slow accumulation, interrupted by long pauses, setbacks, and silence. This kind of exploration does not fit easily into how modern science is organised. Research cycles are short, funding windows are limited, success is often measured in outputs that can be counted and compared. Publications, data sets, visual results. The trench resists these metrics. It does not reward speed, it does not scale easily, it does not adapt itself to human schedules. As a result, much of the trench remains untouched, not because it is uninteresting, but because it does not cooperate. It asks questions back. It forces trade-offs that are uncomfortable to make. Every decision to go deeper means deciding not to go somewhere else. Every descent risks not just failure, but disappearance. There is something revealing in that hesitation. It tells us where our priorities lie and where they falter. We are willing to send machines across the solar system, knowing they may never return because space offers continuity. Signals keep coming, data keeps flowing, failures teach visible lessons. The deep ocean offers none of that reassurance. When it takes something, it rarely explains why, so we leave parts of it unexplored, not out of neglect but out of calculation. And yet, those unexplored depths are not empty placeholders. They are active, functioning parts of the planet. They participate in cycles that regulate climate, recycle materials, and sustain forms of life that challenge our assumptions. They shape the Earth quietly, without asking for attention. Our lack of presence does not diminish their role. This creates a strange asymmetry. The trench influences the surface world in subtle but persistent ways, while the surface world struggles to return the favour in terms of understanding. We depend on systems we barely observe. We're affected by processes we rarely measure. The deepest parts of the ocean operate as background infrastructure for the planet, unnoticed until something goes wrong. Leaving these depths unexplored also leaves gaps in our self-understanding. We like to think of ourselves as a species that explores, that pushes boundaries, that fills in unknowns. But exploration is selective. It follows paths of least resistance, technological compatibility, and cultural momentum. Where those paths do not exist, curiosity alone is not always enough to carve them. The Mariana Trench exposes this selectivity. It shows that exploration is not just about desire, but about alignment. When environments align with our tools, our institutions, and our narratives, exploration flourishes. When they do not, exploration slows or stalls, even if the questions are profound. There is no single moment when humanity decided to leave the deepest parts of the ocean mostly unexplored. It happened gradually through a series of reasonable decisions. One mission deemed too risky, another postponed for budgetary reasons, another redirected towards safer targets. Over time, hesitation becomes habit, and habits shape futures. The depths we leave unexplored today may remain unexplored for generations, not because they cannot be reached, but because the systems required to reach them sustainably never quite take shape. Without continuity, knowledge fragments. Without repetition, confidence erodes. Without long-term commitment, exploration becomes episodic rather than cumulative. This does not mean the trench will remain unknown forever. Technology will continue to advance, materials will improve, autonomy will increase. But unless the surrounding structures change as well, progress will remain uneven. Better tools alone do not guarantee deeper understanding. They must be paired with patience and a willingness to accept slow returns. There is also a deeper question embedded in all of this. Do we need to explore everything? Is leaving some depths unexplored a failure, or is it a reflection of restraint? In an era where human activity reaches nearly every corner of the planet, the existence of places largely untouched by us may carry its own value. Some scientists argue that the trench's inaccessibility offers a form of protection. Limited access reduces disturbance. It preserves systems that evolved without human interference. From this perspective, hesitation is not just pragmatic, but ethical. Others counter that ignorance is not protection. Without understanding these environments, we cannot assess their vulnerability or resilience. We cannot know how they will respond to changes driven by surface activity. We cannot manage what we do not understand. Both perspectives hold truth, and the tension between them remains unresolved. That unresolved tension is itself part of why the trench remains only partially explored. Every descent answers some questions while raising others, including questions about whether the descent should have happened at all. What is clear is that the trench does not demand to be explored. It does not call attention to itself. It does not deteriorate quickly when ignored. It exists independently of our curiosity, following rhythms that long predate human presence. This independence can feel humbling, even unsettling. Much of human exploration has been driven by environments that respond visibly to our arrival. We plant flags, we build stations, we leave marks. The trench absorbs intrusion and leaves little trace in return. It does not acknowledge us. In that silence, we are confronted with limits that are not easily overcome by effort or ambition. Limits set by physics, by economics, by psychology, by the structures we use to organize knowledge itself. The depths we leave unexplored are not simply spaces on a map. They are reflections of what kind of exploration we are prepared to sustain. They show where our curiosity is strong enough to persist through inconvenience, and where it falters in the face of resistance. For now, the Mariana Trench remains a place we visit briefly, cautiously and infrequently. We send machines down, watch what they can show us, and then pull back. We analyze what returns, knowing that much did not. We build narratives around absence as much as presence. There is no dramatic ending to this story because there is no ending at all. The trench is still there. Pressure still builds. Darkness still persists. Life still adapts quietly. Geological forces still reshape the seafloor. None of this waits for us. What we choose to do with that reality remains open. We may develop new ways to observe without intruding. We may commit to long-term monitoring despite the cost. We may decide that some depths are better understood indirectly, through models and inference. Or we may simply continue as we are, hovering at the edge of the deepest places, looking down, aware of what lies beyond our reach. The depths we leave unexplored are not accusations. They are invitations that do not expire. They ask whether we are willing to change how we explore, not just how far we go. They ask whether understanding must always be fast, visible and reassuring, or whether it can be slow, partial and quiet. In the end, the Mariana Trench does not challenge our ability to reach it. We have already done that. It challenges our ability to stay with questions that resist closure, to invest in knowledge that does not immediately reward us, and to accept that some of the most important parts of our planet will remain only partially known for a long time. And perhaps that, more than anything else, is what makes the trench so difficult to explore. Not its depth, not its pressure, not its darkness, but the way it asks us to rethink what exploration means when the world does not open itself easily, and when the greatest unknowns lie not ahead of us, but quietly below.